Dear ladies and gentlemen, let me welcome you to the EAI SGIoT 2020 conference held in this virtual interactive setting. I am Viltara Platzner, the EAI Conference Manager of SGIoT 2020. Unfortunately, I'm not able to meet all of you in person, so I would like to use this opportunity to address the organizing committee, the keynote speakers, the authors, and all the participants on behalf of EAI. I would like to thank all of you for being a part of this conference and for your involvement with EAI. In particular, I would like to thank the General Chair, Yi Bing Ling, and the General Co-Chair, Der Jung Deng, together with the whole organizing committee for their hard and excellent work throughout the whole process of the conference preparation. I would also like to use this message to invite you to join again at the EAI SGIoT 2021. Should you be interested in becoming a part of the next year's organizing committee or technical program committee, please do not hesitate to contact me at my email address below. If you're interested in discussing other possible cooperation, conference, a workshop, or a new event altogether, please contact me at my email address as well. Now, my colleague Michal will present you with what EAI does, who we are, and how you can get involved in our various activities. Thank you for your attention and enjoy EAI SGIoT 2020.
Hi everyone, my name is Michal Dudic. I'm the Community Manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course, and all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work-in-progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Hello everyone, I'm Feng Yaping, the reporter today. The title of my paper is An Enhanced Approach for Multiple Sensitive Attributes in Data Publishing. The contents of the paper are as follows. Part 1 is Introduction, Part 2 is Related Work, Part 3 is Preliminary, Part 4 is Multi-Sensitive Attributes Weights, Clustering and Dividing Model. Part 5 is Experimental and Analysis. Part 6 is Conclusion. The first is the introduction of the author. With the development of the Internet, e-commerce has achieved new growth and has driven the development of the industry, especially since 2011. China's express delivery business has increased at an average rate of more than 50% each year. In the end of 2017, the State Post Bureau announced that China's express delivery had reached 41 billion pieces, ranking the first in the world's express business for four consecutive years. The rapid development of the express delivery industry has improved people's lives to a certain extent and provided greater convenience for people's lives. However, information sharing also leads to the leakage of personal private information, which is becoming serious. For example, there are more and more personal accidents in today's society, such as telephone or text message harassment, kidnapping, fraud. Therefore, studying the problem of privacy protection in data publishing can effectively reduce the risk of personal information disclosure. Our main contributions are as follows. We pointed out the problem of privacy protection data publishing with multiple sensitive attributes. We propose multi-sensitive attributes with clustering and dividing algorithm, which can keep as much available information as possible while maintaining data security. We compare our algorithm with the WMBF algorithm on the real data set. The experimental results show that the release ratio of informant data in our algorithm is higher, above 95%, and the execution time is shorter. Therefore, the published data through our algorithm had higher availability and achieved the effect of personalized privacy protection. Related work. In the study on privacy perceiving data publishing based on grouping privacy protection have developed amounts of classic privacy protection models. S et al. Firstly proposed the K-anonymity model. This model only cut off the connection between identifier and sensitive attributes, but it did not make a corresponding requirement for sensitive attributes, and it was easy to produce homogeneity attack. Then, domestic and foreign scholars continue to improve the model, and L diversity, P sensitive, K anonymity model, AK anonymous model, T closeness model, and other models were proposed. The above privacy protection models are mainly for single sensitive attribute data, but in the actual situation, logistics data publishing involves multiple sensitive attributes, so data owners should pay more attention to privacy leakage for each sensitive attribute when publishing data. Preliminary problem description. Based on different application purpose, population statistics, income statistics, the third party will publish data containing sensitive personal information. Once these data are used by attackers, it will lead to the disclosure of individual information and cause immeasurable consequences, because the fact that different users have different application purposes. We need to protect the published data while meeting the needs of different users, but personalization issues are rarely considered in current data release studies. The multi-dimensional bucket grouping model is still used in data publishing with multiple sensitive attributes, but the multiple dimensional bucket of previous methods has the following shortcomings. The grouping efficiency is lower. The order of selecting buckets is improper, causing data suppressing problems. They cannot meet the user's personalized needs. We propose relevant methods for resolving the above problems in the paper. Problem definition. Definition 1 is lossy join. Definition 2 is multi-dimensional sensitive attributes. Definition 3 is grouping. A group is a subset of the date records in the date table T. Definition 4 is multi-dimensional sensitive attributes L diversity. Definition 5 is D-dimensional bucket. Definition 6 is weights clustering. Definition 7 is weighted average value. It represents the average of the weights or sensitive attribute in each record. Definition 8 is weighted standard value. It represents the degree of deviation between the weight of different sensitive attributes in each record. Definition 9 is suppression technology. Some records that cannot be released or some records that do not satisfy privacy protection are hidden. Multi-sensitive attributes weights, clustering and dividing model. In this paper, we improve the MSB grouping technology to achieve safer and more available data release. The main framework of this paper is shown in figure. It contains of 3 modulars: data collection layer, method layer, and data publishing layer. Data collection layer is obtained through enterprise survey and web coolers. The enterprise survey aims to understand the storage and release of data information in the express company. Web coolers use cooler technology to collect information from website pages. The collected information is built into the original database. Method layer. We firstly divide different records into multiple categories by clustering. Then we build weighted multi-dimensional buckets for multi-sensitive attributes and map the records in the data table to corresponding multi-dimensional buckets. Finally, we select important records by the division method to satisfy the user's different needs. Data publishing layer. By considering the max weight first selection algorithm, we select the data recorded in the multi-dimensional bucket to build a group satisfying L diversity. Then we judge the data that do not satisfy the group for the first time. Finally, the quasi-identifiers of the groups that satisfy the condition are generalized. We suppress the remaining data and publish anonymous tables. Our paper mainly improves the method layer and solves the following problems. According to the weights that users set, we can meet the user's personalized privacy requirements. Our core idea is clustering and dividing. We group the records that satisfy L diversity by adopting record-level strategy to protect data privacy. We further process the clustered data and the remaining data to reduce data suppressing. Finally, we realize the data publishing. Multi-sensitive attributes weights, clustering and dividing model method. Based on the weight of sensitive attribute value in each record, all records are clustered to form multiple clusters, recorded as clustered dataset TC. In each cluster, the corresponding weights of all records are similar or equal, as shown in figure. experimental and analysis. Figure 3A to C gives the release ratio of important data in two algorithms under different parameters. Figure 4A to C shows the additional information loss under different parameters in two algorithms. Figure 5A to C shows the suppression ratio under different parameters in two algorithms. Figure 6A to C shows the acquisition time under different parameters in two algorithms. Conclusion. In this paper, we introduce data publishing from multi-sensitive attributes in logistics and analyzes the privacy perceiving problem of multi-sensitive attributes values based on the idea of multi-sensitive bucketization. We proposed a method of multi-sensitive attributes with clustering and dividing. To satisfy the requirements of users, we adopted the clustering and dividing method to release data. Then we compared the proposed with WLAN algorithm. The experimental results show that the additional information loss and suppression ratio of two algorithms have a little difference, but the release rate of the important data in the proposed algorithms is above 95% and the acquisition time is lower. Therefore, the published data in the proposed algorithm have high availability and achieved the effect of personalized privacy protection. Finally is the reference of the article. Thanks.
Hello everyone, I'm Deng Jie, the reporter today. The title of my paper is Hybrid Encryption Scheme for Secure Storage of Smart Grid Data. The contents of the paper are follows. Part 1 is Introduction, Part 2 is Background, Part 3 is Method, Part 4 is Verification, Part 5 is the Summary, Part 6 is References. Introduction. The first is the introduction of the author. The wide application of smart grid improves the energy utilization rate and improves the power market, but at the same time, it also introduces many security problems, such as data storage, transmission, safety, and other security problems in the process of smart grid data communication due to the special position of power system. How to ensure the security of data storage in smart grid is of greater significance for the safe and stable operation of power grid system. This paper first analyzes the smart grid and its data characteristics, combined with the relevant technologies of cloud computing, gives a data security storage model of smart grid to strengthen the reliability and storage capacity of smart grid. Then, in order to ensure the security of user data storage in the cloud in smart grid, this paper studies the data encryption algorithm and propose a hybrid encryption scheme for smart grid data security storage. Finally, the scheme is combined with the traditional method. The experimental results show that the scheme has the advantages of good encryption and decryption effect, faster execution speed, and high security. It is an ideal scheme for smart grid data security storage. Research background. At present, the standard symmetric encryption algorithm is still used in smart grid, but the number of wireless terminals in smart grid is large and widely distributed, so the key distribution and effective updates is a challenge. In order to solve this challenge, scholars at home and abroad have done a lot of research. Method. Cloud computing technology. Cloud computing is a new data-centric computing method. Its most important idea is to distribute on demand and provide dynamic services. Therefore, advanced computer technology is a pillar of cloud computing. Cloud computing includes virtualization technology, data storage technology, data management technology, and some other unique key technologies. Hadoop distributed file system. Hadoop distributed file system is a distributed file system, which is one of the two core technologies of Hadoop. As HDFS has the characteristics of high fault tolerance and high scalability, it can be designed and deployed on low-cost computer equipment, and applications can read data with higher efficiency, especially for programs with massive data. Data security storage model of smart grid. According to the previous analysis, the introduction of cloud computing technology in smart grid and effective integration of existing software and hardware resources can make power system equipment as constant as possible and greatly improve the processing and storage capacity of smart grid data. This paper mainly studies the security of the data generated by the user in the public cloud storage. Therefore, based on the hybrid cloud structure of smart grid, this paper presents the data security storage model of smart grid under the deployment mode of hybrid cloud, as shown in figure. Hybrid encryption scheme for DSS-MSG. Data encryption technology is known as the core technology of information security, which is mainly divided into symmetric encryption and asymmetric encryption. Data encryption standards, algorithm, and reversed Shamir Adman algorithm are typical representatives. Therefore, in order to better solve the security problem of user data stored in the cloud in smart grid, based on the traditional DES and RSA algorithm, this paper first analyzes the advantages and disadvantages of DES and compares the advantages of triple data encryption algorithm and independent sub-K DES algorithm, improves DES algorithm, and propose a hybrid double DES encryption algorithm. Then this paper makes a detailed study on the method of judging prime number, which affects the operation speed of RSA algorithm. On the basis of not affecting the security of RSA, this paper improves the original method of prime number judgment and proposes a RSA algorithm based on the improved prime number decision. Finally, this paper combines the HDDES encryption algorithm and IPN RSA encryption algorithm to form a hybrid encryption scheme based on HDDES and IPN RSA, which can effectively ensure the security of user data in the cloud. Hybrid double DS encryption algorithm. DS still has many shortcomings, such as its low data transmission rate, not suitable for long-term data protection, and vulnerable to differential key cracking. Therefore, scholars at home and abroad have made many attempts to improve DS algorithm. In this context, they have proposed more influential triple DS algorithm and independent sub-key DS algorithm. RSA algorithm based on improved prime number judgment. In order to prevent the RSA algorithm from being forced to crack, a super long key must be used. Therefore, the more bits of P and Q are, the better. However, the speed of key generation, encryption, and decryption is also slower and slower. For the remaining two attacks, the security of RSA is based on the difficulty of multiplication and integration of large prime numbers, so it is almost impossible to crack, or the cost of cracking is very high. Hybrid encryption scheme for secure storage of smart grid data. The specific process is shown in figure. Step 1. The sender encrypts the plaintext of smart grid data with HDDES key to obtain encrypted ciphertext. Step 2. The sender encrypts the HDDES key information with a public key of IPN RSA to get the encryption key. Step 3. The sender sends the mixed information of encrypted ciphertext and encryption key. Step 4. After receiving the mixed information, the receiver decrypts the encryption key with a private key of IPN RSA to obtain the HDDES key. Step 5. The receiver decrypts the encrypted ciphertext with the decrypted HDDES key to obtain the plaintext of smart grid data. The hybrid encryption strategy based on HDDES and IPN RSA not only improves the efficiency of encrypting user data in smart grid, but also ensures the security of transmission in smart grid. Verification. RSA algorithm based on improved prime number judgment in order to verify the effectiveness of the proposed hybrid encryption scheme based on HDDES and IPN RSA. A detailed experimental comparison and result analysis are made between the proposed hybrid encryption scheme and the traditional hybrid encryption scheme based on DS and RSA in terms of encryption time efficiency and algorithm encryption and decryption performance efficiency. Performance verification and analysis of hybrid encryption scheme. This paper compares the key length and generation speed of the hybrid encryption scheme based on DS and RSA and the hybrid encryption scheme based on HDDES and IPN RSA. Performance verification and analysis of hybrid encryption scheme. security of data transmission process. Before transmission, the data has been authenticated by both parties, and the data to be exchanged has been encrypted, which can ensure the security of the data in the communication process. Security of stored data. The data generated by users in smart grid is encrypted by HDDS and encrypted to produce ciphertext. Before the key and the ciphertext of HDDS are encrypted by IPNRSA, even if the malicious user obtains the ciphertext in the transmission process, it will not be correct because there is no private key of the receiver. To sum up, the hybrid encryption scheme based on HDDS and IPNRSA proposed in this paper can meet the requirements of data storage security in the development of smart grid and has high operation efficiency. The summary. With the further development of smart grid in the future, the scale of power grid is also expanding, and the data in smart grid is also showing a huge increase. The development of cloud computing technology provides a new direction for data storage and processing in smart grid, while cloud computing technology has helped the development of smart grid. Data security in smart grid is also an important issue that cannot be ignored. Because the data confidentiality is an important factor of smart grid data security, this paper makes a more in-depth study on the data encryption algorithm, respectively makes some improvements to the data encryption method, and puts forward two improved encryption algorithm and a hybrid encryption scheme so that the data security can be effectively improved. Finally, simulation experiments and multi-angle analysis are carried out to show that the proposed hybrid encryption scheme can improve the security of smart grid data storage. Of course, the hybrid encryption scheme proposed in this paper can improve the security of data storage, but the data is only pure text and does not cover the encryption and decryption of pictures, audio, and video. In the future, we will continue to study and improve from the above aspects. Finally, is a reference of the article. Thanks.
Hello everyone, I'm Yang Zhang, and the title of my presentation is Classification of Uncertain Data Based on Evidence Theory in Wireless Sensor Networks. It's my pleasure to make this presentation. As we know, in wireless sensor networks, the classification of uncertain data reported by sensor nodes is an open issue because the given attribute information can be insufficient for making a correct classification result. When using the sensor's observation data to carry out the local classification of targets, the sensor's observation data contains a lot of imprecise information due to many interference. For example, many sample data comes from different categories of targets, but they are very similar. That is, the sample data of different categories may overlap, which brings great challenges to traditional target classifications. In the classification task with supervision, the sensor's observation data may be in the overlapping area of different categories of training samples. It's difficult for the traditional voting KN classifier to accurately classify the target at this time. As a result, many new methods are proposed, such as the fuzzy k-nearest neighbor classification algorithm, the evidential k-nearest neighbor algorithm, the improved evidential k-nearest neighbor algorithm. But these methods also have many drawbacks. As a result, in this paper, we proposed a new evidential k-nearest neighbor algorithm. This new method proposed a simple evidence pre-processing method and the framework of evidence theory. This method only considers the expected value and standard deviation of the training sample sets of each category, thereby avoiding the evidence correlation that may be caused by the original evidence editing method. On this basis, by fusing the classification results of the target to be tested in the training sample set of each category, the proposed NEKN obtain a more accurate and the NEKN method always have a more accurate combination result of the target. Our method is based on the Dempster-Shaffer evidence theory. This theory is also known as belief functions theory. In this theory, the frame of discernment omega is a finite set whose elements are exhaustive and mutually exclusive. The power set of the frame of discernment omega represents the set of all possible subsets. That is, given an object X, it can be classified as any singleton element and any set of elements in the power set of omega with a basic belief assignment. This basic belief assignment must satisfy a mapping. We examine two pieces of evidence denoted by M1 and M2. The Dempster's combination rule can be used to fuse M1 and M2. The Dempster's combination rule can be shown as Formula 1. This combination rule provides a simple solution for data fusion problems. In NEKN, in order to overcome the limitations of KNN, our method uses the method of pre-processing training samples to replace the category labels of the original samples with the basic belief assignment. so as to better describe the uncertainty of the training samples in the overlapping regions of the categories. When pre-processing data in wireless sensor networks, Mahana NOMA-based distances are used. This distance avoids discussing the correlation caused by the specific distribution of sample data. At the same time, compared with other distances, Mahana NOMA-based distance can also eliminate the interference of Mahana NOMA-based distance can also eliminate the interference of the correlation between similar attribute data. The processing of training samples have two steps. Have four steps. First, the attribute information of each category of training sample can be used to calculate the center vector of category. The center vector of the category can be expressed as formula 2. Following, the Mahana NOMA-based distance is used to measure the distance between the target and the center. The Mahana NOMA-based distance is expressed as formula 3. The support of the target belonging to category is shown as formula 4, and the final basic belief assignment should correspond to normalized formula defined by formula 5. After pre-processing, the new training sample set with new class label is adopted for the target classification task in the following section. After pre-processing, the next problem to be solved is how to classify the newly observed unknown target based on the pre-processed training samples, different from general classification problem. The category of training sample used here is represented by the basic belief assignment distribution. The evidential mass function provided by the target for the classification can be expressed as formula 6. And when fusion between categories, we use PCR5 combination rules to accurately allocate conflicting information. The PCR5 can accurately distribute the conflict information according to the mass values of the two parts in the conflict, which is very suitable for combing high conflict evidence. The PCR5 rule can be expressed as formula 7. The final section of our paper is experimental results. We assume that the feature data is a 3-dimensional vector, and the observation data and the training data are generated from 3-dimensional data sets and that obey the Gaussian distribution. and its mean and standard deviation have the following distribution as shown in Table 1. We randomly generate 300 test samples and 600 training samples. We use KNN, EKN, IEKN to compare and analyze with NEKN proposed in this paper. The classification results as shown in Table 2. From Table 2, we can see the EKN and IEKN methods are better than the traditional voting KN and can effectively improve the classification accuracy. The NEKN method proposed in this paper can better describe the imprecision of sample data in the overlapping area of the category and improve the classification accuracy of the data by using the basic belief assignment to replace the original category label. Therefore, compared with the EKN and IEKN algorithms, it has a smaller classification error rate, especially when the number of neighbors is small. The performance improved. The performance of NEKN is more significant. Furthermore, NEKN can be found that compared with other classification methods based on K nearest neighbors, it has less sensitive to the value of K nearest neighbor. As a result, our NEKN method is based on evidence editing classification method before identifying and classifying the sample to be tested. This method uses a class label with a basic belief assignment to replace the original category of the training sample, so that the training sample in the class overlapping area can provide more abundant and more diverse category information. From the experiments, it can be found that for imprecise sample data, the NEKN algorithm can obtain better classification performance than other classification algorithms based on K nearest neighbors. Our future work involves the following two aspects. First, finding a more efficient method to estimate the mass value to improve the classification accuracy. Second, designing more credible combination rules to deal with the uncertain data in IoT environment. That's my presentation. Thanks for your suggestions.
I'm happy to attend the SGIoT 2020 and to present my paper titled Machine Learning-Based Security Authentication for IoT Networks. As we all know, a great number of smart devices are being connected to the wireless network, and the Internet of Things plays a remarkable role, like smart home, intelligent medical system, and smart industrial automation. but it also brought a huge challenge to the traditional security method, because the open channel allows for anybody, anywhere, and even anytime wireless connection. So it is open for spy-for attackers, and the overhead of the security algorithm consumes the limited results. So the traditional approach may not enough to protect the communication. As a result, physical layer security has been proposed as an important approach. Some of the problems with up-layer security are shown on the left, such as lower reliability and computational overhead. They are still based on a premise that eavesdropper lacks the power to attack the wireless network. The problem could be in any network, but and not limited to the Internet of Things. On the other hand, physical layer authentication has a great number of benefits, like low computational requirements, lower network overhead, and even does not require trusted third party. We assume in our systems that Alice and sensor Bob I wishes to communicate. But in our system, there is a spy for Eve, who masquerades as Bob I and sends the fake news to the Alice. So Alice should make a decision whether the new signal comes from Bob I or from attacker Eve. Physical layer authentication uses the characteristic of wireless channel to identify different transmitters. Also, it has obviously advantages, but the traditional method used the single static channel property, so they are unsuitable in real communication environments. To meet this challenge, we proposed a long short-term memory-based method, which is used to learn the time-varying feature and to determine whether an attacker or a Bob I is generating the data packet. Let each Bob I donate the channel vector for the channel between Alice and Bob I. We assume the first transmission from Alice to Bob I has been established, and the spy for know when begins to send fake news to the Alice. So the authentication problem can be formulated as equation 1. Here, F is our proposed learning function, and H0 stands for the message belongs to Bob I, while H1 denotes Eve at the transmitter. If the difference between the channel vector is large, it is considered that the signal comes from the attacker or from the Bob I. As we see in equation 3, here we can see the channel model is changed in time. We can see the channel information at the time k plus 1 is equal to the channel information at time k plus Gaussian walls noise. As we mentioned before, the problem is that the wireless channel are time varying. So we need to learn the channel characteristic. As shown in Figure 2, this is our proposed learning authentication model. First, the channel vectors are input the LSTM network, and the data features will be learned by the LSTM layer. Then the classifier will process the output of the LSTM and make a decision. The parameters of the model are updated by the background algorithm. After updating the learning model, used the physical layer attribution. The loss value tends to 0. After we get the well-trained model, during the test dataset will be fed into the LSTM network, and the probability of the channel vectors belongs to different transmitter is calculated. The prediction used in our model can be expressed as equation 5. In this section, we are going to take a look at the experiment setup in an indoor conference room. We investigate the performance of the proposed model. The simulation parameters are on the table 1. Here, we collected the data for each transmitter-receiver combination, and 2 types of samples are involved in our proposed data set. Here, from Figure A, we can see that 2 types of samples, namely Bob 1 and Bob 2, are collected, just shown in Figure A. Each contains 2,000 sampling points. Our approach is compared to 2 methods, namely Gaussian mixture model and the CNN-based authentication method. In order to evaluate the performance of those 2 schemes, we compare the training performance and the authentication accuracy. This figure shows the training performance of our proposed scheme. As we see here, the loss value reached to 0 after 115 iterate. The training performance depends on the communication environment, and we see that increasing the SNR of the sampling in a conference room accelerates the convergence. We see the table 1. We can see here the benefit of using learning approach compared to the method. Our method has a better performance in terms of face alarm rate and authentication accuracy, especially compared with the security method based on Gaussian mixture model. The security rate of the LSTM algorithm is greatly improved. Finally, I will conclude our work. In our paper, we analyzed the challenge of wireless security, and we used the LSTM network to learn the time-varying channel features while performing authentication tasks. We use the long short-term memories to learn the DIMP feature. On this basis, we proposed a machine learning approach to detect the spy for attacker. And our future work will focus on the combination of deep learning and physical layer security. Thank you for your attention.
Hello everyone. Today I will introduce my paper, a secure edge cloud computing framework for IoT applications. Let's show the content. First, I will introduce the introduction and the related works. Second, I will introduce the system architecture. And third, I will introduce system evaluation. At last, I will give my conclusion. So let's begin the part 1, introduction and the related works. In recent years, thanks to the characteristics of low construction and maintenance costs, the Internet of Things and wireless sensor network technologies have become more and more widely used, especially in the monitoring of spatial environments. They have great advantages and application potential in fire alarm, geological exploration, and safe production. However, with the development of wireless communication technology, in general, large-scale wireless sensor networks or large-scale IoT, especially in application scenarios that require extensive monitoring of the environment, the number of wireless sensor nodes and edge sensing devices is rapidly increased. So is the amount of data generated. In this situation, edge computing and cloud computing come into being, and they are two paradigms to implement the Internet of Things. However, for IoT applications, both edge computing and cloud computing have disadvantages. The cloud computing is difficult to shorten the system response time, to reduce the communication bandwidth, and to lower the energy consumption of data centers. And the edge computing is hard to process large amounts of data. What's more, it puts huge pressure on bandwidth resources. Consequently, edge cloud collaboration technology come into being and solve the problems mentioned above. On the other hand, the rapid development of edge computing technology makes people largely ignore the security threats on the edge computing platform and the applications it supports, such as distributed denial of service attacks, side-channel attacks, malware injection attacks, and authentication and authorization attacks. So let's introduce the system architecture. System architecture of the SECC framework is shown in this figure. It is mainly composed of 3 components: wireless sensor nodes, edge computing server, and cloud computing platform. Sensing devices such as temperature sensors, humidity sensors, and image sensors sense environmental changes and send these changes to the edge computing server. Then, the edge computing server and the cloud computing platform collaborate and complete the tasks of the applications running on the framework. Different applications can be deployed according to application scenarios, such as fire monitoring, geological exploration, safe production, and so on. And we implement the edge server as a collection of services, including edge device orchestration, data processing and storage, communication management, authentication and authorization, environment sensing and situation analysis. Okay, so we use a simplified figure to explain the functions of each part. As shown on the right, the role of wireless sensor nodes is as follows. Sensing devices composed of temperature sensors, humidity sensors, and image sensors are put out randomly to form wireless sensor network in order to monitor some special environments. These sensors can sense the dynamic changes of environment in real time and collect some specific data in the environment. In the SECC framework, the edge computing server belongs to the middle layer of the system. During system deployment, small base stations can be deployed on the side close to the wireless sensor nodes as a small edge computing server. It is also possible to use special equipment such as drones in areas where it is difficult to deploy small base stations as the computing servers that can be deployed on mobile to provide edge computing services for the system on the edge of the data. And this figure shows the functions of the edge computing server. In system initialization phase, various monitoring data in the environment collected by the wireless sensor node and the corresponding initialization parameters are uploaded to the cloud computing platform through the relay of the edge computing server. The edge computing server is also in charge of the setting up of wireless sensor nodes on its behalf and on the behalf of the cloud computing platform. In the system operation stage, preliminary processing is performed on the various monitoring data collected in the environment to detect abnormal situations in time. Once an abnormality of a center item or items of data is detected, the cloud computing platform will immediately receive an abnormal report from the edge computing server. At the same time, the controller at the bottom will be driven by the edge computing server to provide emergency solutions for the abnormal situation. And as the figure shows, the edge computing server also provides basic common services such as edge device orchestration, data storage and processing, communication management, authentication and authorization, environment sensing and situation analysis, and so on. Based on the common services, applications can be deployed and developed in a timely manner. In the SECC framework, the functions of the cloud computing platforms are mainly as follows. It has characteristics of large storage space and strong computing power. Therefore, it plays the role of remote data and control center in the system, and its role is to store data and process highly complex data. In some scenarios, the edge computing server and wireless sensor nodes may not be able to provide the corresponding computing power required by the system, and cannot afford the resource loss caused by complex calculations. Therefore, it is used for various complex tasks which are unable to process by edge computing servers. And next, I will mention my security function. At last, as a complex framework consisting of wireless sensor nodes, edge computing server, and cloud computing platform, the whole system have heterogeneous security needs. In order to ensure the system security, we use daisy chain approach. In the SECC framework, we propose to apply the daisy chain approach to satisfy different security needs of the system. In the system initialization phase, the cloud computing platform will first authenticate the edge computing server and establish security parameters used in the following cryptographic operations. Then the edge computing server will in turn authenticate sensors nodes, initializing security parameters used in lightweight message authentication algorithms. Through the daisy chain approach, each part of the system can get a corresponding security level on demand. Okay, that's the part 3. I will introduce the system evaluation. First, from the perspective of wireless sensor node, the requirements for the communication capabilities are greatly reduced, and the advantages of edge computing server in data processing capabilities has been more embodied. Second, from the perspective of edge computing server, compared with the IoT system, it ensures the low latency of the system and has strong computing capabilities. Moreover, it greatly improves security and privacy of the system. Last, from the perspective of cloud computing platform, cloud platform works with the edge computing server. Compared with the traditional cloud computing framework, it reduces the amount of computing on the cloud computing platform, the amount of data uploaded in the cloud computing platform, and the backbone link bandwidth usage. Okay, I will give my conclusion. In this paper, we propose a secure edge cloud computing framework for the Internet of Things. We divide the framework into 3 components: wireless sensor node, the edge computing server, and the cloud computing platform. Through the collaboration of the edge computing server and the cloud computing platform, we can achieve a trade-off between computing capability and response delay. We further implement the edge computing server as a common basic service provider, including unified interfaces to connect wireless sensors and applications to the framework. Basic services such as edge device orchestration, data processing and storage, communication management, authentication and authorization, environment sensing and situation analysis, and so on. To achieve the security in the framework, we propose a daisy chain approach to meet the heterogeneous security requirements of the system. We demonstrate the efficacy of the SECC framework through comprehensive analysis. Okay, that's all my introduce to my paper. Thank you.
Good morning, everyone. I am Wei Lijun from Beijing Jiao Tong University. It's a great honor for me to make this presentation for all of you. The topic of my presentation today is test summarization as the potential technology for intelligent Internet of Things. Here is the outline of my talk, including 4 parts. I will begin with some brief background about extractive test summarization and abstractive test summarization. Second, I will introduce our model design and coverage mechanism. Next, I will show the experimental results. Finally, I will summarize our network. Now, I will start with the introduction. Extractive text summarization selects words or word phrases from the source text to form summarize. First, we have to input a source text. Then we use different methods to calculate the importance of the statement and rank it. Next, we choose physics and sentence with high score and get the summarization. Researchers always use IF, IDF, and text rank to get the score of sentences and characters. IF, IDF is a traditional way that based on statistical methods. Text rank is similar to page rank, which choose characters with high similarity. Extractive text summarization is easy to understand. However, this way has a lot of redundancy and cannot deal well with short source text. Different from extractive method, abstractive text summarization is to produce summaries in a generated way. This figure shows a baseline model of abstractive text summarization. It consists of encoder, decoder, and attention mechanism. Sequence-to-sequence model can compress source text into continuous vector representation with an encoder, and then generated the summary with a decoder. The encoder is a single layer, but directional GRU that can get the sequence vector from source text. The decoder is a unidirectional GRU on each time step t. It receives the word embedding of the previous word and had decoder state st. There are many problems in abstractive text summarization, such as unknown words, out of vocabularies, and repeat words. Next, I will introduce our model design. This figure shows our semantic relevance-based pointer generator model. Our semantic relevance-based pointer generator network contains 5 components: encoder, decoder, attention mechanism, generation probability calculation, and a similar function. Our model is a hybrid among basic attention-based sequence-to-sequence model, a pointer network, and a semantic relevance. It can choose to copy words from the sentence via pointing, while retaining the ability to generate new words from the fixed vocabulary. The generation probability P generation, which is a scalar between 0 and 1, represents the probability of generating a new word from the vocabulary versus copying a word from the source text. Then, P-generation is used to weight and combine the vocabulary distribution P vocabulary, which is used for generating, and the attention distribution, which is used for pointing to the source word WI into the final distribution P-final. To get high semantic relevance between source text and summarize, we add a similar function to our model. One of our training objects is to maximize the similarity score so that the generated summaries have high semantic relevance with the source text. We select last output HN as the semantic vector of source text VT. An easy idea to get the semantic vector of a summary is to feed it into the encoder. However, this method wastes much time. Previous work has proved that we can simply compute the semantic vector of the summary by Vt equal Hn, subtracting Hn from Sm. Repetition is one of the big problems in abstractive text summarization. Moreover, it is a common problem for sequence-to-sequence models. We adapted the coverage model to solve the repetition problem. The idea is that we use the attention distribution to keep track of what's been covered so far and penalize the network for attending to same parts again. On each time step T of the decoder, the coverage vector COT is the mean of the sum of all the attention distributions so far. Then we introduce an extra loss term to penalize any overlap between the coverage vector COT and the new attention distribution. Finally, the coverage loss is added to the loss function, where lambda1 and lambda2 are hyperparameters. Next, I will show the experimental results. Before showing our experimental results, let's see some details about our experiment. We use LCSTS as our dataset. It's a large-scale Chinese short text summarization dataset collected from Sina Weibo, a famous Chinese social media website, consisting for more than 2.4 million text summary pairs. The dataset is divided into 3 parts, and all the test summary pairs are scored manually with relevant scores ranged from 1 to 5. We often select pairs with scores more than 2, leaving 8,685 pairs in Part 2 and 725 pairs in Part 3. In experiment, Part 1 is used for training, Part 2 is used for validation, and Part 3 is used for testing. The Rush metric compiler generated summary with a reference summary by computing overlapping units, and we use it as our evaluation metric. This table shows our experimental results. We compare our proposed model with 3 models. Simple sequence-to-sequence is a based sequence-to-sequence model for abstractive summarization. The main difference between attention-based sequence-to-sequence and simple sequence-to-sequence is that attention mechanism is added to the first one, so it can pay different attention to the source word on each time step. Attention-based sequence-to-sequence is a sequence-to-sequence model with attention mechanism. SRB is an encoder-decoder model that takes semantic relevance into account. This model has a similarity function to attention-based sequence-to-sequence model in order to make sure that there is high semantic relevance between source texts and generated summaries. Compared with other models, we can see that pointer-generator network and coverage mechanism has higher RASH1, RASH2, and RASH-L score, so this model plays an important role in getting more coherent summaries. Finally, I will summarize our work. First, we propose an architecture that can get the summary in an automatically copied or generated way. Second, our coverage mechanism solves the problem of repetition to some extent. Finally, when our PGCS is applied to many intelligent scenarios of Internet of Things, we can get more benefits about computing and network transmission. Thank you for your attention. If you have any questions, I will be happy to answer them.
Greetings, let's just begin. And we'll talk about hierarchical edge computing today. And our work is to focus on computing capacity allocation. That means we do not consider storage resources and other factors, because that for edge computing we can use some classes of databases from other places, so we may not use the local storage. So we just talk about computing capacity resources today, and we try to solve this problem with energy efficiency evaluation. That means we not just only consider the loss portion, and we also take energy efficiency into consideration. And so this is the whole architecture of hierarchical edge computing. So this is a cloud. Let me choose a pen. So this is a cloud, and we have deep nodes and shallow nodes. So deep nodes and shallow nodes are the edge layers, and we have devices in the bottom. So data may come from devices to shallow nodes, and if shallow nodes could handle the data, and it will such as turns into storage or just return the computing result. And if shallow nodes is overloaded, or it can't do this work in time, it will offload this work to deep nodes, and deep nodes will do that work. Also, deep nodes may have some data flows to cloud that indicates that cloud could do some work to have static data or something else. So what our job is to find how to allocate computing resources between deep nodes and shallow nodes. So let's assume that our budget is limited, is finite. So how much resource should we put on shallow nodes, and how much resources should we put on deep nodes? This is question. So let's come to see some variables and a constant. We assume that W is the workload of a certain task. So maybe if there are 2 tasks, the workload should be 2W. And mu is the serving rate. It's just an abstract of a variable, so we have some specific mu in follow as follow. Mu t indicates total serving rate in shallow nodes, and it's linked to deep nodes. Alpha is the distribution coefficient. It shows that how much resources we put on the shallow and how much we put on the deep. Mu s and mu d is the serving rate of shallow and deep nodes, and d is the delay tolerance. We should make sure that the waiting time and the processing time should no more than d. N is the quantity of shallow nodes under a deep node. It means maybe a deep node is linked to some shallow nodes, and its quantity is n. And lambda is the arriving rate of a shallow node I. So we consider that the tasks come to shallow nodes are several queues or several flows. Each shallow node has its queue or flow, and the tasks just arriving in this queue are just a flow to shallow nodes. L is the queue length in shallow nodes. That means we have cache or say queue in shallow nodes. So if the shallow node is busy, this task may wait for some time, but how much it can wait is depend on the queue length. So L is the queue length, and lambda J I is the arriving rate from shallow node I to deep node J. It means maybe shallow nodes could not handle this work, so it has to offload some work to deep node, and from this shallow node to its deep node, this this flow or this is lambda ji, and the Cij is a binary coefficient. It equals to 0 or 1 to indicate whether deep node I and the shallow node J has link relationships. So let's come to next. We have some constraints and some expressions. Just let me explain. W divided by mu is task waiting time, so it should be no more than D. And mu S and mu D, as we have said, is serving rate in shallow and deep node. So alpha is distribution coefficient. So alpha may be equals to 0.2. It means that we put 20% resources of this task on a deep node, and the other 80% of the resources on shallow nodes. So shallow nodes, it equals to 1 minus alpha n times mu t, and mu d, we notice that there is a n in this expression. It means maybe, for example, we have a deep node. It links to 3 shallow nodes. Each shallow node put 20% computing resources on this deep node. So the deep node should be 20% times mu t n times 3. So now we got mu d, and t is the longest waiting time when a task is in a shallow node. So it maybe have to wait L times, and for itself it also needs some time for shallow node to process itself. So there should be L plus 1 times W divided by mu S, and we know T should be no more than D. So we got L limited. It means that we have a limited length or finite queue in shallow node cache. And let's come to next. And lambda ji should be 0 if lambda I is no more than mu S. And if the shallow node is overloaded, it should offload some work, some tasks to deep node. So it should be lambda I minus mu S. So this is mu S. There are 2 situations. We just talk one of them. The other is that shallow nodes do not offload to deep nodes. So we won't talk about it. Oh, sorry. This lambda ji is deep node J and shallow node I. I'm sorry. So lambda J is the arriving rate of deep node J. So we got this, and Cij is a coefficient. It's binary. Still remember? It's 0 or 1. Now we have some simplification to simplify this problem. So if the parameter is growing smaller, it means that the possibility is actually going down. Well, we have this Rj. It means that the loss portions, and of course it should be always bigger than 0 or equals 0. So there is a mass function, and so the loss should be its arriving rate n minus what it can deal with, and the loss is it has to abandon. We just cause some of it Cij equals to 0, we just don't consider them, and there is only some items that is larger than 0. we just write them out here. And so the m is always that is no more than n, because we may cut down some items which Cij equals to 0. So we got the expressions here. And notice that m is always no more than n. And so we got loss here, and we try to figure out the loss, the relationship between the loss and alpha. So we turn it to a function of alpha. You know that there is a summary of lambda, and this is independent with alpha. It's not alpha just do not have any influence on it. So we just so if at this moment, if we have a certain lambda, it is definite, and we have this. Why it should be divided by the summary of the lambda? Because we want to have a normalization, and just we have this, and we can take its derivative. So we can find its derivative. We can see m is no more than n. This will be no more than 0. So we can see the R alpha is going down as you grow of the alpha. There are already some articles focused on energy, but they just consider to cut down the whole energy by just adjusting this network, this structure. But maybe in some scenario we couldn't cut down some nodes in some places, because maybe in this place it must be a node here, and so we just we couldn't change the p idle. That means the energy, the power when this system is idle. We just could find a way to decrease this p working. So p is equal to CV square f, and this is an expression from CMOS or FET. Well, we can find these expressions in a Texas instruction. I put it in the references. So it may be just we grow up the frequency, the performance, and the power, the energy of a CPU should grow. But we could not grow the frequency without other factors, because of there is an effect named gate delay. So if we want to get higher frequency, we need some higher voltage, so V should be growing up too, and we just need this trend of the function. So it sounds like a cubic function. So we use a cubic function to simplify this problem. And so we have n shallow nodes and a deep node. This is a cluster. You know, a deep node has n shallow nodes linked to it. So we have this expression, and we do some normalization here, and we got an energy function. So the result is that we add a coefficient beta to weigh the loss and the energy function. So if we consume more energy, of course we got more performance, we got better performance. And if we want to save the power, if we want to have save more energy, the loss maybe grow a little. And there is our simulation, because there is still time limit. I couldn't talk too much, so I just talk one of them. The blue line is the energy function we have, and the yellow line is a yellow-orange line. The right line is the loss function we have, and purple line is that G alpha. So there are some conditions in our simulation. Lambda is always, you can see lambda is here, and the summary of lambda is always bigger, is larger than the system tolerance. That is to say, we always have loss here. We always have loss here, so that we can have a method, have some way to see this loss. And n equals to 3, that means there are 3 shadow nodes linked to a deep node, and beta is equal to 0.8. It means that there are 80% that we consider the loss, and there are only 20% we consider the energy. But we can see that here there are 20% we just consider take energy into consideration, but this is only 30% energy compared to we do not consider energy evaluation. So this is very efficient, and we also have some simulation on what if n were virus, or what if beta were virus. Well, I do not have the picture, the simulation here, but we found that if a deep node has more shadow nodes, it will has a better performance, and beta should be adjusted by the actual scenario. And so maybe in the future we can do some work on how to adjust this system dynamically, just change its links, relationship, and so on. And thanks for watching.
Hello, experts and scholars. I'm one of the authors of this paper. Now I will explain the paper to you. This paper title is Research of Offloading Decision and Resource Scheduling in Edge Computing. I'm the speaker. My name is Li Zhiyuan. Next, I will explain this paper from 4 aspects. First of all, I will introduce the research background of the paper. Secondly, I will explain the system architecture and the modeling process. Then I will give an explanation of the simulation results. Finally, I will give this paper makes a summary. The increasing in the increasing scale of the Internet of Things pose challenges to the energy consumption, transmission bandwidth, and processing delay of centralized cloud computing data centers. The cloud computing data centers is moving from the center of the network to edge nodes with lower latency, namely edge computing. In the field of edge computing, offloading decision and resource scheduling are the hotspot issues. As for offloading decision and resource scheduling problems of single-cell multi-user partial offloading, the system model is also firstly established from 4 aspects: network architecture, application type, local computing, and offloading computing. Based on the system model, the optimization problem of resource scheduling is modeled, where the solution is hard to be found. Third, the deep reinforcement learning method based on police gradient is selected to establish the SPB-DDPG algorithm that can solve the problem. Then, in order to solve the practical problems, the algorithm is set up with the state and the action for interaction, as well as the environment for generating new state and feedback reward view. Finally, an appropriate interaction step is writing for the edge computing resource scheduling problem by combining with the original deep reinforcement learning algorithm. We also evaluate the proposed approaches by relevant experiments. The complexity and effectiveness of the results are validated. The system consists of 3 models: operation model, optimization model, and offloading model. Based on the offloading of mobile computing architecture, the multiple user equipment through the calculation of base station, mobile edge server, and the system are linked together in a single-cell multi-user scenario. Base stations use TDMA model to enable communication, and the time is divided into several time slots. When user has a computer-intensive application to process, it sends results requests to the system through base station. Afterwards, the system makes smart decisions about whether to migrate an application and which parts need to be migrated to the edges. Once the system has decided to migrate, 3 phases need to be performed in sequence. like this picture. User equipment sends data to base station will uplink channel. A mic receives the calculated offloading data of user equipment from base station. The results are sent back to user equipment through the downlink channel. Based on the deep reinforcement learning approach, the paper further proposed a single-cell multi-user partial offloading based on deep deterministic police gradient algorithm superior to the traditional police gradient reinforcement algorithm, which is specially designed to resolve the optimization of user device partition migration in the single-cell multi-user scenario. The algorithm has two parts, actor and critic. The critic network uses the deep intensive learning algorithm based on will functions, which can output the corresponding Q and V according to the state S and action A, where the variable A can be expressed as the expression. Therefore, A can be approximately expressed as the expression. At this point, the critic network can be provide actor network with a weight function for gradient rise and update. The paper is based on the Python edge structures in the network environment simulation to achieve the edge computing resource scheduling and tasks offloading system network architecture. In the simulation model, the algorithm is used to optimize the results. For comparison, the reinforced algorithm and the minimal offloading scenario are chosen as baselines. Specific simulation parameters are shown in left figure. During the training process, the sixth round began using memory data to train neural network. Then the new data will cover the original database. In the right figure, the reward will begin to change since the 16th round and the algorithm complete convergence when it comes to the 19th round. In a word, our algorithm has a good training effect and convergence rate is rapid. With the increase of cell user equipment, the computing power of edge server is limited, and many tasks need to be calculated locally. In the left figure, the total energy consumption of the scheduling scheme based on the algorithm is lower than the other two schemes. And the maximum of time delay that all users can tolerate increases. Many tasks can be calculated by offloading tasks to the edge server. As a result, local computing energy consumption will be reduced. In the model figure, compared with the optimization scheme based on reinforced algorithm, and implement minimal offloading scam. The total energy consumption of the scam proposed in this paper is lower. With the increase of the edge server computing capacity limit, many tasks can be offloaded to the edge server for computing. So the total energy consumption of user equipment will be reduced. In the right figure, the total energy consumption of the scheduling scheme based on our algorithm is lower than the other two schemes. It indicates that the upper limit of edge computing server's computing capacity has a certain threshold value. If the edge server's computing capacity exceeds the threshold value, the energy consumption of user equipment will not be reduced. Finally, in this paper, an offloading decision and resource scheduling optimization algorithm based on deep reinforcement learning is proposed, which can reduce the energy consumption in traditional edge computing problems and improve the resource utilization. Meanwhile, the conventional reinforcement algorithm combined with DQN was used to model the actual scenes of edge computing through SPB-DDPJ algorithm, and the problem is optimized and solved. Besides, its computational accuracy and complexity are improved compared with the other modes. Finally, the advantages of our methods are proved by the experimental simulation, and service preloading scheme is proved to the effective. On the other hand, we admit that there are some limitations in this paper. For example, optimization is mainly based on energy consumption and is not applicable to scenarios that are more time sensitive or integrated. We will concentrate on it in the future. At the same time, some factors should also be considered, such as other deep reinforcement learning algorithms, and it is an important research direction. That's all I'm talking about. I appreciate that animals reviewers who provide constructive feedback on earlier work of this paper. And thank you for listening.
Hello everyone, my name is Liu Sai. I'm from China, Beijing Jiao Tong University. My paper's title is An Industrial-Grade API Secure Access Gateway in the Cloud Edge Integration Scenario. Okay, let me introduce my paper to you. In recent years, the Internet of Things technology has developed rapidly. Due to the large number of devices at the edge, the wide distribution range, and the complex environment, cloud computing and edge computing failed to fully consider security risks at the beginning of the combination. And the traditional protection methods can no longer fully meet their security requirements. The establishment of a new cloud edge integrated security system is of great significance for ensuring the data and privacy of Internet users. This paper first investigates the current status of traditional network security and analyzes its inherent shortcomings. We also analyzes the organizational structure and main advantages of the Zero Trust network. We designed a security certification system that meets the needs of cloud edge integrated applications. The API Security Access Gateway, part of the system, is designed and implemented according to the type of client access request. It is equipped with multiple authentication methods. It also released the functions of reverse proxy, load balancing, flow control, log audit, analysis and monitoring of microservices. We finally developed a supporting UI management tool based on VUE. This design provides a new set of secure access solutions for client and microservices, which has produced good industrial benefits. It is of great significance to promote the development and popularization of cloud edge integration. The highly dynamic and heterogeneous environment at the edge of the network and the numerous and complicated data on the cloud have exacerbated the difficulty of network protection. Research on cloud and edge security technologies can effectively prevent security issues in data, privacy, network, and off-site storage brought by products in service. And ensure data and privacy security for Internet users. Therefore, studying the security of cloud edge integration application is the primary prerequisite for the further development of the Internet of Everything system, which is of great significance for promoting the development of cloud edge integration. The Zero Trust model has improved the level of security to a certain extent, and even solved the contradiction between security and ease of use. Therefore, in combination with the security authentication requirements of the Cloud Edge Integrated Computing Service platform in this project, we have designed a network security architecture based on comprehensive identification and controlled by a Unified Identity Authentication Center, and a Trusted Access Gateway, as shown in this figure. The client may need to call multiple service interfaces to complete a business requirement. The API gateway can classify, forward, and organize external requests, avoiding cross-domain requests, complicated authentication, difficulty in reconstruction, and firewall restrictions. In this paper, we built an Nginx development environment based on Kong server and configured a relational database PostgreSQL. The gateway implements a reverse proxy for client requests based on Nginx. It reduces the pressure on the back-end web server and improves the response speed. In addition, we have also expanded the functions of the API gateway in terms of identity authentication, load balancing, flow control, log auditing, analysis and monitoring. In terms of authentication, we designed and implemented basic auth, KAuth, JWT auth, OAuth2, LDAP auth, and IP restriction. In terms of flow control, we have request termination, rate limiting, request size limiting. As for log audit, we have syslog, fail log, and HTTP log. Based on the VUE framework, we encapsulate the back-end API secure access gateway and other monitoring software services. Modularize the functions of the API gateway. Use Element UI framework to lay out and display all pages. The gateway uses a ring load balancer, and the addition and deletion of back-end services are handled by the gateway, without receiving updates from DNS. Ring load balancing is accomplished by configuring upstream and target entities. By default, the ring load balancer uses a weighted round-robin scheme and an IP address-based hash algorithm to implement load balancing. In terms of monitoring alarm, it provides an open and a complete monitoring solution by integrating the Prometheus system. Users can obtain the true running status of services and applications, such as CPU share. For some complex situations, it can also use service discovery capabilities to dynamically manage monitoring targets. In addition, intuitive information such as system operating status, resource usage, and service operating status can be directly obtained by connecting various tools. That's all the gateway's functions. As can be seen in Table 1, the average RTT time to complete all kinds of certifications is less than 0.023 seconds, which is less than the reaction time. This indicates that the proposed system is applicable within the real world and performs well. In addition, the data processing performance of the scheme shown in Table 2 fully meets the parameter requirements of load balancing. In summary, this article mainly studies the cloud edge integrated security authentication method under the guidance of the concept of zero trust. It analyzes and summarizes the current cloud edge and integration process and the research status of related authentication technologies. This paper designed the Cloud Edge Integrated Platform Security Authentication System and the industrial-grade API Security Access Gateway. At the technical level, it has completed the construction of index-based API Security Access Gateway and related functions such as identity authentication, load balancing, reverse proxy, log audit, analysis and monitoring. And more. Dashboard is designed to facilitate user management. After testing on the edge computing platform of our project, the utility and the security of the proposed scheme and design have been verified, which greatly meets the complex security certification requirements in the Cloud Edge Integrated Computing Application Platform. Okay, that's all my presentation. Thank you.
Hello, everyone. Today, the topic of my presentation is an OSPF-based backhaul protocol for 5G millimeter wave network. The outline of my presentation are 5 parts. They are background, contribution, protocol design, simulation results, and the conclusion. Let's see the first part, background. High capacity, large bandwidth, high speed, and low energy consumption have become the main trends of wireless mobile communication networks in the future. The fifth generation mobile communication system is definitely the mainstream of development. As one of the important components of 5G communication system. 5G millimeter wave network is also a research hotspot, considering the distribution and scheduling of data transmission in access and backhaul network. The number of nodes and the link allocation, it is very helpful to improve the overall network device quality and improve the user experience by designing active routing protocols. So, the improved performance, we propose an O1 shortest path first OSPF based backhaul protocol for fifth generation 5G mobile communication millimeter wave network. We call it OBPG protocol. So what's the millimeter wave integrated access and backhaul network? It has the following characteristics. One of the characteristics is access and the backhaul resource sharing. Although the sum of available resources on the access and backhaul links of millimeter wave IABN is fixed, the allocation of available resource between access and backhaul can be freely changed. So, as to meet the needs of the network's instant service transmission, another characteristic is free and flexible network deployment configuration. It can use self-backhaul integrated with access to simplify the network establishment and transmission stage. It can use millimeter wave communication. This OBPG protocol is based on the open shortest path first protocol for backhaul routing. From OSPF, OBPG is more suitable for the backhaul routing problem of millimeter wave IABN. Let's see the picture 1. The picture 1 is OBPG protocol construction. From the last picture, let's see the second part protocol design. For the backhaul protocol, there are two main functions, which are backhaul paths establishment and backhaul data transmission. Therefore, the proposed OBPG can be divided into two main stages, which are backhaul routing path establishment stage, the user access, and the backhaul data transmission stage. On the one hand, in the backhaul routing path establishment stage of OBPG, time division multiple access (TDMA) is used for access to the network. Then, within these allocated time slots, integrated small cell stations (ISCS) can establish the backhaul routing path to the fiber-enabled small cell station (FSCS) based on the OSPF routing protocol, such that each ISCS can hold the whole network topology and establishes at least one backhaul path to the FSCS. On the other hand, in the user access and the backhaul data transmission stage, based on the whole network topology abandoned in the backhaul routing path establishment stage, each ISCS can run a coloring algorithm to allocate the user access time slots in the backhaul time slots in a distributed method. And the ISCS can pooling and scheduling the associated UEs to transmit data and backhaul them to the core network. And an important part of OBPG is OSPF. OSPF is a relatively mature and very stable dynamic routing protocol. With the help of the OSPF protocol, a millimeter wave macro base stations can establish a shortest path from any macro base stations that is not connected to the optical fiber to the macro base stations that is connected to the optical fiber. Among them, the algorithm we use is the Directional algorithm, which has been improved to a certain extent in the traditional algorithm. After the protocol design, the main contributors to this paper are as follows. An OSPF-based backhaul protocol for 5G millimeter wave networks is proposed. A coloring method used to allocate transmission time slots was proposed. The simulation results show that when the blocking probability is 30%, when the number of multiple associations with users and the millimeter wave macro base stations increases, the network throughput performance is about 20% higher than the performance of the number which is one less. The next part is simulation results. Let's see the picture 2. The picture is 5G scene construction. It can be seen that 10 millimeter wave macro base stations are deployed within a range of 20 multiplied 20. This millimeter wave macro base station have 7 millimeter wave macro base stations that are not connected to optical fibers, and 3 millimeter wave macro base stations that are connected to optical fibers. For 3 UE, the probability P of the directional link being blocked is simulated by random numbers in the program. Now it's simulation 1. Assuming that the deployment of the base station has been determined, K refers to the number of base stations to which the user is connected. When the K is 2 and K is 3, and the number of UE is continuously added to the network, the following curve can be obtained. From the picture, the increase of users will inevitably lead to an increase in the amount of data, and the user access is more frequent and huge, which requires higher throughput of the network. We can see from this picture the throughput is higher and higher. As for the simulation 2, where the number of base stations M is 8 and M is 12, and the number of user equipment n is 15 attested, you can see that the higher the probability of the link being blocked, the more data needs to be retransmitted, which greatly increasing the amount of data generated in the network is in line with our expectations, reducing the transmission efficiency, making the network require higher throughput to carry the normal operation of access and backhaul. We can easily see in this picture the throughputs are higher and higher with a blocked probability. The last part is conclusion. This paper is a simulation study of OBPG. First, in the introduction section, the current status of 5G millimeter wave networks, the current research status at home and abroad are investigated, which leads to some shortcomings in the routing protocol of 5G millimeter wave backhaul network. The OSPF protocol is linked to try to solve this problem. Next, the specific combination of the OSPF mechanism and the operation of the 5G millimeter wave backhaul network are introduced, including in the establishment stage and the transmission stage. Not only this, but also the combination of slot allocation, coloring method, improved Jacobson algorithm with theoretical foreshadowing. It was implemented in simulation according to the process submodel and simulated more realistic 5G scene, such as 3 types of base stations, directional communication, blocked probability, and other factors involved. It also observes the influence of factors such as the number of users or blocking probability under other circumstances on network throughput. It was found that OSPF can well adapt to the construction of 5G millimeter wave access and backhaul integrity networks, and the purpose and significance of the research are abundant. In summary, this paper contributes the OBPG routing algorithm, which mainly refers to OSPF, and integrates a coloring method and other mechanisms. It has a good performance in simulation and has reference value. Of course, it can be more perfect in the subsequent research, because this paper only mainly studies the network throughput requirements under the protocol, and there are many indicators that can describe network performance, such as delay, round-trip time, utilization, and more. This is my presentation. That's all. Thank you.
Ladies and gentlemen, it's my honor to have this opportunity to share something with you about routing metric in wireless mesh network. There are 4 sections: background, contribution, simulation, results, conclusion. Here I want I want to tell you something about routing metric in wireless mass network. Since its birth in the 1960s, the development of network technology has been extremely repeated. Traditional wireless local area network provide stable network connection and larger amount of data traffic for billions of people around the world. With the rapid development of economy, users put forward higher requirements on coverage, communication qualities, and carrying capacity of wireless network. However, in many cases, the wireless basic network can't be fully covered or is difficult. Therefore, wireless mass network with the advantage of flexible deployment, multi-hop transmission, wide coverage is developing rapidly. Wireless mass network is a new network technology that derived from ad hoc network and inherent part of wireless local area network. Next, I will share with you something about hop metric. Hop metric is a hop count is a number of data forward from the source node to the destination node. The pace with the fewest hop is the transmission pace. The metric has the advantages of simple implementation and low overhead. However, the shortcomings of hop metric are prominent. Hop doesn't take into account of link delay, interference, load, packet loss rate, and other factors. So hop metric is likely to lead to poor performance of the selected pace. Expected transmission count ETX user expected number of transmissions that successfully transmitted to their destination node as a measure of link quality. ETS considers delay and packet loss rate. As you can see, the ETS of link I can be calculated by the following formula. Symbol PF and PR respectively represent the uplink and downlink packet loss rate of link I. Expected transmission time (ETT) is developed from ETS. ETS considers the influence of packet loss rate, delay, and bandwidth on routing quality. The pace with the small is the sum of ETT is the set pace. The ETT of link I can be get by the following this formula. Simple as represent the average data length. B represent the current actual data transmission rate. Following is the link priority metric. RP is very interesting. RP considers the business priority level, like link widths are determined according to the number of priority of data passing through the link over a period of time. Each kind of data has a real-time priority. The pace error of the RP can be calculated from this formula. Following is airtime link metric. ALM. Airtime link metric is an approximate measurement method. Airtime's main purpose is to reduce the difficulty of specific implementation and interaction. Airtime link metric considers the transmission rate, channel quality, and packet loss rate. The airtime link metric can be get by this formula. Simple O represent channel access overhead, including frame header, transmission sequence, channel access protocol frame, and so on, and depend on implementation. BT represent the number of bits contained in the body of a data frame. R represent the data rate used under the current link condition when the data frame is transmitted. EF represent the frame error rate of data frame. Following is the multi-rate routing metric. This routing metric is very interesting. MRM considers the influence of inter-stream interference, delay bandwidth, and packet loss rate on routing quality. MRM is derived from ETT. The pace P, the MRM of pace P can be get by this formula. Following is a conclusion of routing metric. This routing metric is suitable for single channel routing, single channel. In single channel network, the most important consideration for routing metric is the delay and packet loss rate. Of course, interference, noisy, transmission rate, channel bandwidth, and so on will also affect network quality. But the most important is packet loss rate and delay. This is some more routing metrics suitable for multi-channel. In multi-channel network, delay and packet loss rate are still research hotspot. However, compared with single channel, multiple channel has its own characteristics. Intra-stream interference and inter-stream interference are researched hotspot for multi-channel network. At the same time, several inter-stream interference and inter-stream interference will greatly reduce network throughput. Of course, there are also scholars studying other aspects such as node load and bottleneck channels. As we all know, there is often more than one gateway in a network, so the choice of gateway is very important. Currently, in routing metric, the bandwidth and load of gateway are mainly considered. The capacity of gateway is limited, and if the gateway is selected with a heavy load, the network throughput will be limited. Therefore, the load of the gateway is also an aspect that should be considered in multi-gateway network routing metrics. There are few routing metrics suitable for multi-gateway mass networks. Following this is the contribution of this paper. This article. The article investigates many routing metrics and sought out these routing metrics. Two routing metrics are simulated. The pros and cons of these two routing metrics are compared. OLSR provided the optimal pace based on the number of routing hop, create ad hoc node, and the channel physical layer and MAC layer all use the Wi-Fi protocol. There are 50 nodes renamed distributed in area. In the same network case, change the number of nodes to observe changes in throughput and delay. This is the throughput of two routing metric. By comparison, when the number of nodes is small, the throughput of distance routing metric is larger, and the performance of distance routing metric is better at this case. When the number of nodes is larger, the throughput of distance routing metric is smaller than the throughput of hot, and the performance of hot is better in this case. For packet delay, when the number of nodes is small, the total delay of distance routing metric is small, and the performance of distance routing metric is better in this case. When the number of nodes is larger, the total delay of distance routing metric is greater than the total delay of hop, and the performance of hop is better in this case. Following this is the conclusion. As the technology of wireless mesh network, routing metric should be diversified. The appropriate routing metric should be selected for different case for different network quality requirement. It is also necessary to select a proper routing metric based on the source of the requirement. At present, the consideration of routing metric is relatively single, often focused on factors such as delay, packet loss rate, and link quality. Therefore, it is a good research direction to combine routing metrics and channel allocation schemes.
Ladies and gentlemen, I'm Lei Shuning. I am delighted to be here and make a presentation of my paper, Design and Implementation of FPRP on FPGA for Internet of Things. My presentation will be divided into these 5 parts. Firstly, I will show something about the background. With the rapid development of communication technology and the improvement of people's communication requirements, Internet of Things has become an important research hotspot of nowadays network. MAC protocol has great influence on the performance of wireless sensor networks and is one of the key protocols to ensure efficient communication for Internet of Things. The FPRP protocol started in this paper is a MAC protocol based on computation. The current research shows that the performance of CSMA and CA protocol and Aloha protocol may deteriorate when the network density becomes high, while the FPRP has the advantages of flexibility and efficiency, and it is more suitable for the ad hoc network. To guarantee low energy consumption and high efficiency for the nodes of the Internet of Things, how to design and implement the Joint Contention and Reservation-based protocol, FPRP, becomes a significant issue. It has been proved by practice that the FPRP protocol adopts the 5 steps handshake mechanism, which does not produce slot waste and effectively solves the problem of hidden terminal and non-isolated net deadlock. However, the FPRP protocol does not take into account such problems as unfair slot allocation caused by different node loads, low channel utilization, and excessive access delay due to single-channel communication. Here, I list 2 examples of improvement research, which have a good solution to simplify the complexity of FPRP system implementation and improve slot utilization. FPGA has a strong real-time capability to process signals in real time. In addition, it realizes various functions through software programming oriented to chip format instructions. Therefore, the original design scheme or original functions of the system can be improved by modifying the software code without changing the hardware platform, which is of great flexibility. Therefore, using FPGA as a platform to implement FPRP protocol is very convenient, practical, and effective. How to use FPGA to implement FPRP protocol is the key content of this paper. The main contributions of this paper are as follows. Firstly, proposed a design scheme to realize FPRP protocol, proposed to divide FPRP protocol into several modules to realize different functions, including clock counting module, algorithm module, reservation result generation module, data transmission module, and so on, and realize various functions with Verilog language simulation. Secondly, carried out the simulation design for clock counting module, algorithm module, and reservation module, successfully realized the receiving and sending of double nodes, and obtained a correct output waveform, proved the feasibility of the whole scheme. Then I will show some basic knowledge of FPRP. FPRP divides the channel into frames, and this figure shows the frame structure. Each frame contains two stages, the reservation stage and the data transmission stage. The nodes that need to transmit message initiate the reservation process with probability P in the reservation stage. Once the contention is successful, the node will occupy the certain slot for data transmission. After that, if the node still needs an information slot, the slot resource is recomputed in the next reservation phase. Normally, as shown in the figure, when node 3 initiates a reservation and does not receive the CR frame from node 2 and node 4, it can send RC frame to them. After receiving RC frame, node 2 and 4 sends RA frame to node 3 and node 5. Node 5 receiving RA frame sends PP frame to node 6. Then node 6 knows that its one hop neighbor node 5 will not compete for this slot. So the computation probability P of node 6 can be increased in its two-hop network. However, when contention occurs, for example, if node 2 and 4 send R frame for reservation at the same time, then node 3 will feed back CR frame after receiving multiple R frames, so that everyone gives up computation. There is another situation, is that when nodes 2 and 4 send out the reservation process at the same time, but they have no common neighbor node, then they will not receive CR frame. At the same time, they reserve to the same slot, but do not know the existence of each other. As a result, a non-isolated deadlock is formed. In this situation, it is necessary to send EP frames to avoid contention. The FPRP protocol uses Bayes-based algorithm to calculate the probability P to send messages. Bayes-based algorithm requires each node to adjust the reservation probability P by estimating the number of neighboring computators, and there are different algorithms for the number of surrounding computators according to success or failure of the reservation. In order to realize FPGA design and implementation, according to MAC protocol module system architecture shown in this picture, FPRP protocol is divided into 5 key sub-modules: clock counting module, reservation module, data transmission module, algorithm module, and reservation result generation module. In this paper, the relationship among the reservation module, algorithm module, and the clock counting module is refined into several parts as shown in this figure. Next, I will show the simulation results. According to the design scheme, this paper gives the verification results of the total module of single-node reservation receiving and sending, and the verification result of two nodes. Firstly, I will explain the result of the single node. For the total top-level module of the reservation sending module, in the case of no contention, RR frame, RC frame, RA frame, and so on are successfully transmitted in corresponding slots, but CR frame is not sent. When contention occurs, a contention-enabled signal is set to simulated contention. It can be seen that when the contention occurs and the R frame has been received, the module sends and outputs the CR frame. As for the reservation receiving master module, for the incoming frame, firstly, the module judges the frame type, then calls the corresponding frame receiving submodule to receive. After receiving, output the receiving completion-enabled signal. These completion-enabled signals are connected to the sending master module, according to which the sending master module sends the next frame to complete the reservation. Then I will show the result of the two-node validation. It can be seen that the external node inputs the signal value to node 1, then the outputs of node 1 are sent to node 2 as its inputs, and the outputs of node 2 is those of the total module. In this paper, the FPGA implementation scheme of FPRP protocol is presented. The design and simulation ideas of algorithm module, clock counting module, and reservation module are detailed, and it is proved that this scheme is feasible. However, this verification is between two nodes, and the node cannot receive multiple R frames. In this situation, CR frame will not be sent forever. In order to simulate the contention, I customize a collision occurrence signal for simulation, but this is only limited to simulation, which is not applicable to the actual situation. In the following work, the result of fractional generation of algorithm module can be improved, and the remaining unrealized modules such as reservation result generation module and the data transmission module can be fully realized. Besides, for some reasons, this paper does not calculate the maximum clock frequency and other parameters of the program, and hope to improve it in the future research work. That's all of my presentation. Thank you.
Hello everyone, my name is Li Xinru. I'm from Northwestern Polytechnical University. It's a great honor for me to have the opportunity to present a report here. My paper title is An Optimal Multi-Round Multi-Slot Hello Reply Directional Neighbor Discovery Algorithm. I will introduce it from the following 5 aspects. The directional wireless ad hoc network combines the directional antenna and the wireless ad hoc network. It has the characteristics of strong independence, high damage resistance, and high spatial reuse, and can optimize the transmission performance of the network. It's widely used in the military field, disaster relief, and other occasions. Neighbor discovery is the premise of node network communication. Neighbor discovery effection will directly
affect the network performance, with the purpose of shortening the total neighbor discovery time. This paper focuses on the slot optimization of neighbor discovery hello reply phase in directional wireless ad hoc network. This paper proposes an optimal multi-round and multi-slot hello reply algorithm, theoretically proves and deduces the neighbor discovery time and the discovery round of this algorithm, which effectively reduces discovery time. Moreover, this multi-round and multi-slot hello reply algorithm is combined with existing protocols to verify its feasibility and neighbor discovery efficiency. Combined with the simulation results, the simple fitting expressions of discovery rounds and discovery time are given. In the hello reply process, the master node establishes the connection between the two by sending hello to slave node and receiving slave's reply. In each round of hello reply, a hello slot and several reply slots form a frame. The frame length is determined by a reply slot number. A frame is also called a round, and the round number is also a variable, depending on the number of neighbors and reply slots. After the start of hello reply, the master node first sends hello to slave node in hello slot, which contains the discovered slave nodes and the reply slot number of this round. When the slave receives hello, it will check to see if it has been found. If not, the slave node will randomly select one in reply slot to reply. Otherwise, it will remain silent in this round. After the slave sends a reply message, there are three possible states for a reply slot: successful, idle, or collision. Compared with the neighbor's number of nodes, when slot number per round is set to high, it will cause slot waste, while when slot number is set to low, it will cause slot confliction. It will cause slot conflicts and incomplete neighbor discovery. In both cases, the discovery time is longer. Therefore, an improved hello reply
Hello everyone, my name is Wang Jianwang, and I come from Beijing Jiaotong University. I am glad to be able to attend the meeting. The topic of my thesis is QR code-based efficient entry method for intelligent files of Internet of Things. Next, I'll introduce the paper from the following 5 aspects. In the first part, I will introduce the background. In recent years, with the development of information technology, archive management has gradually shifted from traditional manual management to intelligence. However, due to the limitations of archives, some file archives cannot be completely replaced by electronic archives. Therefore, there is an urgent need for a solution to achieve an efficient and intelligent file entry program while retaining complete file information. The Internet of Things, as a network of intelligent identification, monitoring, and management, has been widely applied in the fields of medical treatment, transportation, and logistics. Therefore, if the Internet of Things technology can be applied to file management, a smart and efficient file management system can be constructed. QR code, as one of the key technologies of Internet of Things, has been applied in smart library, smart locker, electronic payment and other fields in early years because of its fast decoding, high data storage, strong error correction ability and other characteristics, and has achieved very good results. Therefore, applying it to an intelligent file management system also has a certain application basis. The main work of the current file management system is mostly aimed at efficient retrieval and safe storage after electronic files have been obtained, while ignoring the necessity of traditional paper files in the process of converting paper files into electronic files. The time cost and equipment cost required, so there is still some room for optimization. In the second part, I will introduce related work. Intelligent file management system has always been one of the focuses of research. Some scholars have used the new framework to improve the existing document management system and increase the usability of the document management system. Other scholars have used the advantages of multithreading and message queues to reduce the cost of the file management system in response to the high cost of the existing file management system. In addition, the security of the file management system is also extremely important, and some scholars have conducted research on it. Our work aims to reduce the efficiency of converting paper documents to electronic documents, and we have designed an appropriate method to improve the efficiency of document input. In the third part, I will introduce our approach. In the process of program design, we use the C++ programming language. In order to simplify our program, we used the open-source image processing library OpenCV 3.2 to locate the key areas in the captured image, and the open-source barcode recognition library ZBAR to extract the file information. According to different functions, we divide the designed program into 4 modules. First, we extract the key information of the archive and encode it with a QR code. Then, attach the obtained QR code to the surface of the original file. In order to improve the efficiency of collection, multiple files are overlapped, and the QR code information of each file is not blocked. After that, multiple files were scanned at the same time to complete the collection of information. Next is pre-processing. Since the input image has a high resolution and contains a lot of useless pixels, if it is processed directly, it will consume more CPU resources and time. Therefore, bilinear interpolation is used here to adjust the original image. In this way, on the one hand, the amount of image data is reduced, on the other hand, some small noises in the image are eliminated. Binarization is an important step of pre-processing. The quality of the processing result determines whether the QR code area and interference area can be accurately located. Here, we compare the traditional method with our method to illustrate why our method works better. For traditional binarization methods, first, use the following formula to convert the image into a grayscale image, and then use the OTSU method, or a local adaptive thresholding method to process the grayscale image to obtain a binary image. The following figure shows the process of traditional binary image acquisition. It can be seen that the binarized image obtained in the above 3 cases contains a large number of interference regions, which does not meet our requirements. In order to solve these problems, we have improved the traditional methods. First, the original RGB image color space is converted to YCRCB space, and then the image is separated into channels Y, CR and CB. Since the channel Y represents brightness, we have abandoned it to avoid the effect of illumination unevenness. The QR code area and interference area in channel CR and channel CB are clearly colored, so these two channels are used to replace the original grayscale image and are processed using OTSU algorithm. The results show that both channels can separate the QR code area from the background area, as is shown in figures. Further, in order to reduce the interference region in the image and combine the advantages of the two channels, we reverse the binary image obtained through the channel CR, and then carry out XOR operation with the processed image and the channel, so as to obtain the binarization image containing less interference region. Through the above operations, we can visually see the target area and the background area. Because there are obvious color mutations at the boundary, we can perform contour detection based on this feature, and obtain a binary image containing only the outline of each area. Here we test the commonly used edge detection operators Sobel operator, Laplace operator, and Canny operator respectively. The results show that the Canny operator detects the edge of the contour and the pseudo-edge. Area positioning. Since the target area has obvious quadrilateral features, we use the Find Contours function in OpenCV for contour detection. By setting specific parameters, we can get the outermost contour of each target area, record the position of each contour coordinate, and then we use the approx_poly_dp function to fit the obtained discontinuous contours to obtain a complete polygon and record the coordinates of its vertices. Area filtering. Next, we filter the obtained polygons and delete the contours that do not belong to the QR code area. Since our target area has an approximate quadrilateral shape, and the shapes of other interference areas are mostly irregular, we can do some processing work based on this feature. First, we obtain the smallest closed rectangle based on the vertices of each contour. Then we calculate the perimeter of each contour, the enclosed area, and the perimeter and area of its rectangle. Table 1 and Table 2 show some measurement data. By analyzing Table 1 and Table 2, we found that, for the target area, the perimeter of the contour is not much different from the perimeter of the corresponding closed rectangle. However, for the interference area, the contour circumference is half of the circumference of the enclosing rectangle. For the target area, the contour area is approximately equal to the area of the corresponding closed rectangle, but for the interference area, the areas of the two are different or both are zero. Therefore, based on this information, we discarded the rectangular areas with smaller length and width. Then, calculate the ratio of the area of the enclosing rectangle to the area of the outline. If the ratio is approximately 1, it is the target area. If the ratio is too large, it is an interference area. QR code correction. Since ZBAR has poor support for deformed QR codes, it cannot directly identify the area after positioning. Here we use perspective transformation to deform the target area. First, we calculate the coordinates of the corresponding points in the original image according to the coordinates of the vertices in the contour, and sort these vertices, and then use perspective transformation to deform the corresponding areas in the original image. After such processing, we finally got the standard QR code area. QR code recognition. We call ZBAR to detect the corrected QR code area, and record the QR code information to the corresponding location in the system. The fourth part is the experimental results and analysis. This is some specific parameter settings during the experiment, including the size of the convolution kernel of the filter, the filtering conditions of the interference area, the input resolution and output resolution of the image, and the setting of related thresholds and binarization. We selected 30 groups of images taken from different angles, each group including a different number of QR codes, to test the misdetection of the target area and the correct rate of QR code decoding. Table 3 and Table 4 show the test results. It can be seen from Table 3 that our algorithm has a good recognition effect on various QR codes, but in some cases, QR codes cannot be recognized sometimes. After analysis, we found that when the document pocket is not empty and the shooting angle is too oblique, it will cause the QR code in the captured image to appear different degrees and types of distortion, which may cause the QR code to fail to decode. Therefore, our algorithm is suitable for multiple QR code recognition with little deformation. As shown in Table 4, in most cases, our algorithm can detect and separate all areas containing QR codes. For the extra interference area in the detection, we can eliminate it by detecting whether there is a QR code. For the QR code area that is missing in the detection, it is recommended to place the QR code in the center of the image when shooting the image to help reduce the distortion of the QR code area. The fifth part is the experimental conclusion and future work. In this paper, we first proposed the use of QR code to store key archive information, and design a method of simultaneously inputting multiple pieces of archive information, to solve the problem of low efficiency of document management information inputting in the Internet of Things era. The results show that, compared with the existing method of entering one file at a time, the method we designed can simultaneously enter the information of multiple files at the same time, and the number of simultaneous entries can also be adjusted, which has a good expansion. So our method not only improves the efficiency of file information entry, but also provides new solutions for data entry in the existing intelligent file management system. Of course, our method still has some limitations. In our experiment, the QR codes of all file labels are of the same type and the same size, and when entering specific files, you may encounter situations where different types of files are simultaneously entered. In addition, when multiple files are overlapped, the types and degrees of deformation of different QR codes are not consistent, and how to correct the deformed QR codes becomes very challenging. Therefore, we will conduct further research on these issues in future work to build a more intelligent file management system. Finally, the references of this article are listed below. That's all, thank you for listening.
Hello everyone, my name is Sun Ke from Northwestern Polytechnical University. Today my topic is an optimal channel bonding strategy for IEEE A02.11be. Today my presentation will divide into 5 parts. First is background. About channel bonding. The conception of channel bonding technology is proposed since IEEE A02.11n. 2 consecutive 20 million Hz subchannels can be bonded to form a 40 million Hz channel bandwidth channel for data transmission, in order to improve the transmission rate and throughput. Channel bonding has a greater development in IEEE A02.11be, where the number of bonded channels increased to 16, and the most differences is that the bondable channels in IEEE A02.11be are no longer required to be consecutive, which means channel bonding strategies in IEEE A02.11be will be more flexible. Therefore, a better channel bonding strategy is needed to take advantage of flexibility of channel bonding in IEEE A02.11be. And about existing channel bonding strategy, that is, when the state accesses the channel, it bonds all current idle channels for transmission. It will cause a problem. What about when access the channel, there are only a few idle channels available, and if waiting for a few microseconds, it is very likely that the state can be bound a great number of channels. About this paper's contribution, in this paper, we use the flexibility of channel bonding in IEEE A02.11be. A channel bonding strategy based on optimal stopping theory is proposed. The simulation results show that, compared with the traditional EDCA strategy, the data transmission complete time of large film is shortened by more than 40%. As for this paper's key idea, the total transmission time is divided into accessing time and sending time. This article analyzes the accessing time and sending time separately through statistic method, then applied optimal stopping theory to get the channel bonding strategy that minimizes the total transmission time. According to channel condition and the size of package to be sent, a threshold is dynamically obtained. After accessing the channel, add a judgment. If the number of available channels is not less than the threshold, select to send. Otherwise, give up this access opportunity. As for details, to consider the general optimal stopping problem, we need to consider the benefit and the cost of the problem. But in fact, the object of the optimal stopping problems in this paper only need to consider the cost, because once starting send, no matter how many channels are bounded to send, the final income is consistent, that is, complete the sending of the film, and the cost of channel bounding problems only consider the time cost, that is, users want to transmit as quick as possible. So we divide time into two segments with a sign of stop waiting and start sending. As shown in picture, before accessing the channel and stop waiting, there will be multiple attempts to access the channel, and the time for access to a channel is accessing time. Therefore, a set of random variables can be obtained. It follows a certain distribution, so we can get the waiting time. Exactly. After start sending, the sending time is a function related to the film size and the number of successful bounded channels. But the number of the successful bounded channels is based on access rate, so that we can make the total sending time the shortest by control how many channels it started sending. As for the simulation, in order to make the research content of this paper more concise, this article will analyze the scan of a basic service set in wireless local area network as shown in Table 1. There are 3 node types. The 1 AP, 1 C stations, which means stay with channel bounding conception, and several S stations, which means stay without channel bounding capability, only working on single channel. In the process of accessing the channel, AP and C station can bound all current idle channels for transmission after accessing to the channel, while traditional S stations can only send and receive on the fixed channel, and S stations are evenly distributed on all channels. This article only considered uplink data transmission scenery, that is, C stations and S stations connect to access channel for data transmission, and the AP is only responsible for data reception. As for simulation result, first is transmission time. As the pictures show, the smaller the threshold, the shorter the time to wait for accessing the channel, but the slower the speed to sending films. Therefore, the larger the film to be transmitted, the more suitable it is to wait for more channels to be bounded. On the other hand, the busier the channel, the more time it takes to bound multiple channels. The status proposed in this paper is better to the traditional channel access method on the different channel condition, especially when the package is large. As for the threshold in different channel condition, on the different channel busy condition, the larger the film to be sent, the greater the threshold. Among the abnormal results, just like the yellow line, there are no steps to raise because although the channel is idle, the average sending length of S stations is very short, and C station can access the channel easily, but not easy to bounding too many channels. As for conclusion, through simulation, the time taken to transfer films using in this channel bounding strategy can be obtained, which is smaller than the traditional channel bounding and a fixed threshold channel bounding strategy. Moreover, the error between the simulation and the theoretical results is within half time slot, so it has a higher reliability. In the analysis of this article, the channel is assumed to be very idle situation. There is no conflict, no impact on each other, and the business of each channel is exactly the same, and only one C station is considered. This has only a certain reference value for the resolution of practical problem. In further step, we will apply the knowledge of game theory to analyze the behavior of a large number of C stations and analyze the impact of different type of C station on the channel. Based on this article, we will find a more general optimal stopping rule. Thank you.
Hello everyone, I'm Hu Xiaojiao. The topic of my report is a probing and probability-based two-round directional neighbor discovery algorithm. Introduce the proposed agreement from 5 aspects: background, contribution, protocol design, simulation results, conclusion. The first, background. In the wireless directional self-organization network, not only the network transmission performance is greatly improved, but also has good anti-interference performance, which makes it have better communication performance in military communications and emergency communications. However, in the wireless communication system, it is necessary to first solve the problem of inefficient discovery caused by the difficulty of neighbor node discovery and the conclusion of neighbor nodes. Neighbor node discovery is a key part of wireless ad hoc networks, and effective neighbor node discovery algorithms are indispensable to most MAC protocols based on wireless network. When the time slot is fixed, the number of neighbor nodes will greatly affect the efficiency of neighbor node discovery. So, improving the efficiency of neighbor discovery is an extremely important process. Contribution. Neighbor node discovery algorithm based on probability adjustment is proposed. It learns and verifies the mode of estimating the actual number of neighbor nodes based on the occupied standards of the scan time slot, and adjusts the probability of the next round of neighbor nodes competing for time slots, which improves the speed and efficiency of neighbor node discovery, make it possible to find as many neighbor nodes as possible within a fixed time, reduce time slot conflicts, and improve time slot utilization. The algorithm has good probability and can be applied to most wireless ad hoc networks, especially in the case of a large number of nodes. This algorithm has obvious advantages. Protocol design. The DTRA protocol divides communication into 3 phases. Each phase is composed of several time slots of the same size, and each time slot is divided into several mini slots of the same size. The fourth stage is the scanning discovery stage. In this stage, the node discovers neighbor nodes and solves the problem of neighbor node discovery and maintenance for the next 2 stages. This shows that the neighbor node scanning phase of the DTRA protocol is extremely important. However, when the neighbor node table is established in the scanning phase, the working efficiency of the protocol is low due to its specific scanning modes. There are far more neighbor nodes than communication time slots. The probability of conclusions is extremely high, resulting in a low efficiency for nodes to find neighbor nodes around. As shown in Figure 2, when the number of neighbor nodes is much greater than the number of current time slots, the probability of node conclusion increases. Result in few neighbor nodes are discovered by the current beam. Therefore, in a fixed time slot, how to reduce net conclusions, improve time slot utilization, and improve neighbor node discovery efficiency is a key. We proposed an algorithm, a probing and probability based two-run directional neighbor discovery algorithm (PPTR). In the scanning phase of DTRA, the number of time slots T is fixed. So, the improved number discovery algorithm in this paper is to increase the number scan from 1 round to 2 rounds. As shown in Figure 3, the first round of free competition, and according to the number of various time slots after the first round of scanning, estimating the number of neighbor nodes n. Then adjust the first round according to the relationship in the second round between the number of neighbors and time slots. The number nodes compete for the time slot probability PS, so that in the second round the slave node competes for the time slot with the probability PS, thereby maximizing the neighbor node discovery efficiency. This algorithm has 2 key parts. The first part is how to estimate the number of neighbor nodes. Here are the calculation steps for neighbor estimation. Probability of a certain time slot becoming a successful time slot in a fixed time slot PE. Time slot failure probability PS. Then the idle probability is naturally calculated PF. Then the probability of several success, failure, and the number of failed time slots P. This is the probability after the flower. Calculating the reason from the result is obviously a posterior distribution problem. According to the posterior distribution, when the value of P is reached to maximum, the estimate value of adjusted nodes is the best. Therefore, we can estimate the number of neighbors. The second key point is how to estimate the probability of time slot contention. Studies have shown that when the number of nodes and the number of time slots are equal, the time slot utilization is the highest. Therefore, we guess that setting the time slot probability as shown in the figure can achieve the same effect. When n slot nodes compete for SRES slots, TS with probability PS, and nodes decides to participate in the competition probability, this P content. When n nodes decide to compete for TS slots, the probability that any slot can become a successful slot is as follows: P success. When n slot nodes compete for TS slots with probability PS, the probability that any slot can become a successful slot is as follows: this P slot success. Then you can get the expected number of successfully discovered nodes. The higher the efficiency of neighbor discovery, the higher the expectation of the node. Finally, we can verify that the probability P is correct. Therefore, we divide all the scales into two parts. The first part replaces the neighborhood interruption, and the second part competes for conversion with probability, and finally finds that there are gradually more neighborhood interruptions. The last part is the simulation verification of the algorithm. The simulation results are the average value of 10,000 simulations on the C++ simulation platform. We assume beam alignment in the simulation. This picture shows the change of the original protocol and the improved protocol with the increase of the number of network nodes. It can be seen that the improved algorithm is maintained within a certain range and has good stability. This simulation diagram shows the effect of the different time slots occupied in the first stage on the number of final neighbors found. It can be seen from the figure that the fewer time slots in the first stage, the greater the number of node discovery. This because there are more time slots for the probabilistic response of the second stage. So that, what's the impact of dividing the second stage into several rounds on the final result? Please take a look at this picture. It shows the result of dividing the second stage into 1, 3, and 4 equal parts. It can be seen that the results of the 3 are similar. Therefore, the division of the second stage has no effect on the result, but the multi-stage division increases the network overhead. So, the second stage doesn't need to be divided again. Conclusion: a probing and p-probability-based two-round directional neighbor discovery algorithm is proposed. 2. Improve the efficiency of neighbor node discovery. 3. As the number of neighbor nodes increase, the performance of the proposed algorithm is more stable and the advantages are more significant. Finally, the simulation results turn out that descent protocol increase on average 81.3%, when the number of nodes increased to 5 times the number of times lost. Thank you.
Hello everyone, I'm so honored to be here today to make my presentation. The topic of my paper is a data scattering algorithm based on lane distance in directional aviation relay network. I will make it in 5 parts, as the outline shows. The first part is background, and then the contribution, protocol design, simulation, results, and the conclusion. First, let's start with the background. First, I want to talk about my network, that is Directional Aviation Relay Network, DARN. There are two types of nodes in DARN, namely air relay nodes and ground nodes. Among them, the air relay nodes have the advantages of high flying altitude, usually up to several kilometers, line of sight with most ground nodes, and large communication coverage up to a distance of kilometers. It can relay data for a large number of distant ground nodes. And as the unequal link distance. The unequal link distance means that there are multiple ground nodes in the directional working beam of the air nodes, and the line of sight distance between each ground node and the air nodes is unequal, resulting in unequal data propagation delay. Communication delay expansion problem. As the distance of the wireless communication link becomes longer, the propagation delay of the wireless signal, which can be ignored, becomes longer, which can no longer be ignored compared with the data transmission delay, resulting in the problem of reduced efficiency of multiple access protocols. And the second part is contribution. In this paper, a data scheduling algorithm based on link distance is proposed, aiming at the problem of low data transmission throughput caused by unequal link distance between aircraft relay nodes and ground nodes in a directional aviation relay network. When the network traffic is zero-rated compared with the distributed scheduling algorithm, the algorithm named link distance data scheduling proposed in this paper improves the network throughput by 7.4%. And let's talk about the third part, is protocol design. The MAC frame is divided into 3 stages as shown in Fig. RAR collection phase. The air relay nodes and the ground nodes exchange data transmission requests in a trigger response manner. Firstly, the air relay nodes invert some ground nodes in the trigger frame that the downlink service is about to be sent. After being informed by the trigger frame, ground node responds to the response frame and prepares to receive the downlink service. If the ground node has uplink service that needs to be sent to the air relay node, regardless of whether the node is included in the trigger frame, the response frame is immediately answered after receiving the trigger frame. And in the response frame, the local node's uplink service request is sent to the air relay node. Forecast stage. After the air relay node receives all the uplink and downlink service transmission requests, it allocates resources and broadcasts the results of the resource allocation to all nodes in the network. The air relay node sends the broadcast data packets routed by this node to the ground node, and allocates time slot for the broadcast data packets routed by the ground node. Data stage. According to the results of resources allocation algorithm, the data transmission between the air relaying node and the ground node is completed. The duration of the uplink and downlink is dynamically adjusted according to the business situation. And the key idea of the paper is as following. The downlink has higher scheduling priority than the uplink. If the downlink data can be transmitted preferentially, the storage unit at the air relay node can be released first, and then it is convenient to store the uplink data information newly sent by the ground node. The long-distance link traffic has higher scheduling property than the short-distance link. If the air relay node preferentially send data to the long-distance node, it can optimistically send data to close nodes within the time slot for the long-distance node to reply. And then is the link distance data schedule. In order to enable the receiving end of the uplink data to obtain the maximum throughput within a certain period of time, the packet sending time of each STA is reasonably arranged so that the AP can continuously receive and process data without gaps. According to the time information collected in the RAR phase, the STA's time for sending the package can be reasonably arranged. It can be seen that the LDDS algorithm has a very high working efficiency at the air relaying node. The air relaying node first sends data according to the far and near rule and starts receiving the uplink data without gaps at the end of the downlink data. According to the different distance between ground nodes and air relay nodes, this data scheduling algorithm arranges their respective packets sending times in advance so that air relay nodes can work at full capacity. The X of the figure is the time-consuming system of the algorithm, and the Y is the number of packets sent. All nodes send a unit-length data packet. It can be seen from the figure that the performance of the two algorithms is the same in the initial AP downlink phase, but in the AP uplink phase, the time required by the new algorithm is significantly better than the comparison algorithm. This is because after the LDDS algorithm enters the data transmission phase, the STA will prepare to send packet uplink. In the DS algorithm, the uplink and downlink are completely separated. The STA must wait for the AP to complete the downlink frame before it can start the uplink transmission. This will cause all the packets to be sent or are in the link transmission state during the start of the uplink phase, and the AP will have a period of idle time, resulting in a waste of time. The LDDS algorithm proposed in this paper makes good use of link inequality information to arrange STA to send packets in advance, avoiding the time resource consumption of AP here. The X of the figure is the packet production rate, and the Y is the network throughput. The maximum link distance in this text scannery is 214 km. It can be seen from the figure that the LDDS algorithm can reach the saturation point of network throughput faster than the LDDS algorithm. It is easy to see through the principal analysis table of the LDDS algorithm and the DS algorithm when the maximum link distance of the network is consistent with the transmission time required for the network data, and the LDDS algorithm will have the most obvious throughput gain compared to the DS algorithm, and also reach the maximum throughput of the network. When the network traffic is saturated compared with the DS algorithm, the network throughput is improved by 7.4%. The X of this figure is the maximum link distance in the network, and the Y is the network throughput. Under the condition that the total traffic to be transmitted by the network is fixed, when the distance between the links in the network is small, the LDDS algorithm transmits all the service in one time, which is roughly equal to the service transmission time, and there is no additional link propagation delay. We'll get the maximum network throughput. When the distance between the links in the network is large, the LDDS algorithm will increase the time it takes to transmit network service, and the DS algorithm will increase the long-distance propagation cost. However, the total time consumption of the LDDS algorithm will always be less than that of the DS algorithm. So the network throughput of the LDDS algorithm is always better than the DS algorithm. The last part is conclusion. A data scattering algorithm based on link distance is proposed in the Directional Aviation Relay Network, which blurs the uplink and downlink stages of the overall network and keeps the relay nodes in working state as much as possible. Therefore, the air nodes and the ground nodes can communicate efficiently, improves the utilization rate of the network resources, and increase the network throughput. And simulation results shows that using this data scattering algorithm in direction aviation relays networks, the network will have better throughput. Thanks for listening. That's all. Thank you.
Ladies and gentlemen, it's a great pleasure to attend this conference. The topic of my presentation is Latency-Oriented OFDMA Random Access Scam for the Next Generation WLAN IEEE 802.11be. This is the outline of the presentation, and the first part is the introduction. In recent years, the global communication business grows rapidly, and WLAN becomes one of the most important data technologies. Lots of real-time applications such as online game, VR, are becoming increasingly sensitive to delay. Scams for latency guarantee need to be well designed. Therefore, delay guarantee is considered as a key issue of the next generation WLAN standard, IEEE 802.11be. This paper is proposed an OFDMA-based random access latency guarantee scam. And the next part is motivation. OFDMA is used in WLAN, and there are total N RUs and M states. Among M states, there are MDS states with delay-sensitive traffic. Due to random access, the successful possibility of states with delay-insensitive traffic is the same as that of the states with delay-sensitive traffic. Therefore, delay-sensitive traffic cannot be well guaranteed. In order to protect delay-sensitive traffic, some RUs are reserved and allocated to states which have delay-sensitive traffic. Then states with delay-sensitive traffic will have higher successful transmission possibility than that of states with delay-insensitive traffic. Therefore, delay-sensitive traffic can be well guaranteed. The next part is the proposed algorithm for latency guarantee. The main procedures are shown in this figure. After a successful backhaul, according to the collision status of RUs in the last trigger frame interaction, as well as the traffic rate, AP will estimate ME. ME is the number of states which will have delay-sensitive data to send. Then AP will configure appropriate NDS. NDS is the RU number for latency-sensitive states. And AP will send data trigger frame to states. Swift after receiving trigger frame, the states will send applic data. Another swift later, AP can respond BACK to states. The proposed algorithm is divided into two parts, estimation and configuration. Estimation is to get ME, and configuration is to set NDS. This table shows notations used in the derivation. M is the number of all stations. MDS is number of stations with delay-sensitive traffic. ME is estimated number of stations with delay-sensitive traffic. N is number of the all RUs. NDS is the number of RUs for delay-sensitive traffic. NS is the number of successful RUs within NDS RU. Ni is the number of idle RUs within NDS RUs. Nc is the number of collided RUs within NDS RUs, and T is time. And there are three states for a single RU. They are successful, idle, and collided. A successful RU indicates that only one state chooses RU, and an idle RU means no states choose this RU. And a collided RU means that at least two states choose this RU. So we need to estimate the number of states which will have delay-sensitive data in the next trigger frame reaction according to the situation of RUs. So there will be two types of the delay-sensitive states. They are the states which choose collided RU and didn't choose collided RU. The states which choose collided RU, they must transmit data next time. And the states which didn't choose collided RU, it will not clear that whether these states transmit data next time or not. For the states which choose collided RU, Cha pointed out that a collided RU is caused by 2.39 states on average. Then the number of these states can be estimated at this. For the states which didn't choose collided RU, we assume the traffic rate is lambda I, and the received packet number is Ri. The next transmission time is T. If Ri is not larger than lambda T minus 1, state I must send data. If Ri larger than lambda T minus 1, state I must not send data. Then we can define two indicative functions in order to present it more intuitively. So finally, ME can be estimated as follows. And in the configuration is to set NDS. After estimated ME, the number of states which will have latency sensitive data to send, we need to allocate appropriate NDS RUs for these states to maximize access efficiency. For a particular RU, the probability that a state transmits successfully in this RU is shown in this formula. Because there are ME delay sensitive states and NDS RUs for delay sensitive states, the expected successful delay sensitive state number is shown as this formula. Then access efficiency can be calculated by this formula. Then we can find that the maximum efficiency achieved when NDS is equal to ME. This figure shows the frame interaction of the proposed algorithm. We can find that It is compatible with the framework of IEEE 802.11 standards. And the next part is the simulation result. The simulation scenario is single cell. There are 100 states and 72 RUs. And the traffic rate is variable through time. The detailed configuration information is shown in this table. This figure shows the throughput of delay-sensitive states. IEEE 802.11ax perform UORA with total 72 RUs. The transmission opportunity for each state will be the same, and the throughput of each state is equal. Therefore, the throughput of IEEE 802.11ax has a linear relationship with the number of the delay-sensitive states. In the case of fixed RU mode, when the number of delay-sensitive is small, the throughput will be higher as the delay-sensitive state number grows. And if the number of delay-sensitive is larger, the collision among delay-sensitive states will be very serious and the throughput will descend. It can be found that the maximum throughput is achieves when the RU number is equal to the number of delay-sensitive states. The proposed dynamic RU algorithm can allocate appropriate RUs according to the current situation. So the throughput can be well guaranteed whatever the number of delay-sensitive states is. And this figure shows the utility of throughput. White coefficient 0.8 is set for delay-sensitive states, and weight coefficient 0.2 is set for delay-insensitive states. Then we can get the utility of throughput, UT. From this figure, we can find that the dynamic RU adjusting algorithm has the highest utility. It is 19% higher than that of IEEE 802.11ax, and it is 86% higher than that of fixed 30 RU smooth. This figure shows the delay of delay-sensitive states. As the result shows, the delay of IEEE 802.11ax is also a constant value because of its computation fairness for each state. For fixed 30 RUs, as the number of delay-sensitive states grows, the delay will be larger and larger due to the limited RU resource units. However, when the number of delay-sensitive is small, dynamic RU algorithm can achieve almost content delay due to the enough resource units, and the system will be saturated when the number of delay-sensitive states is larger than 50. Therefore, the delay will increase if the delay-sensitive state is more than 50. This figure shows the utility of delays. 0.8 is set for delay-sensitive states, and 0.2 is also set for delay-insensitive states. We can find that the proposed dynamic RU algorithm has the lowest utility of delays among these algorithms. It is 21% lower than that of IEEE 802.11ax, and it is 15% lower than fixed 30 RU moves. And the next part is the conclusion. The proposed dynamic RU adjusting scheme outperforms the other methods on both throughput and delay. UT of the proposed algorithm is 19.69% higher than that of IEEE 802.11ax, and is also 86.14% higher than that of fixed 30 RU modes. UD of the proposed RU dynamic RU algorithm is 21.39% lower than that of IEEE 802.11ax, and it is also 15.93% lower than that of fixed 13 RU mode. And that's all. Thank you.
Hello everyone, my paper is a multi-channel anti-collision algorithm in multi-reader RFID networks. Then I will introduce my paper. First, we need to learn the outline. There are background contribution, protocol design, simulation results, and conclusion. Now we will learn the background. The development of IoT. In recent years, the Internet of Things is developing rapidly and becoming increasingly popular. It has been found everywhere in our daily life, such as the electronic collection system free of parking fees, the card swiping system on trains, the smartphone system, and ACT. According to official statistics, global Internet penetration increased from 20% in 2030 to 65% in 2019. The complete radio frequency identification system, including radar and electronic tag application system, at the core of IoT technology. RFID stores all kinds of data of physical infrastructure into tags, so as to integrate physical facilities and data center into an integrated platform and make the IoT run better. An introduction of the problem. In RFID technology, the core part is tag identification technology. The rate of tag identification determines the performance of RFID system. The configuration scheme of single reader is difficult to overcome new challenges. in many new scenery. It's required to complete the identification of a large number of tags in a short time. Therefore, there is a configuration scheme of balanced multi-readers in RFID system. But in the multi-reader RFID system, there has a new form of collision called multi-reader collision. In the process of tag identification, multi-reader system will cause a lot of packing loss, and of course, identification fail due to this collision, which will seriously affect the performance of the system. In order to solve the problem of low efficiency of multi-reader collision process in this environment, this paper proposes a multi-channel blocking reader anti-collision algorithm for multi-reader RFID system. The following describes the basic principle using the anti-collision grouping strategy to group the readers that may collide optimally, so that different groups of readers can run at different frequencies or time slots, so that the collision between readers will not occur, which can avoid collision and make greater use of challenge resources, so as to improve the label recognition efficiency of the multi-reader system. Now, the Extinct technology has DCS algorithm. This is a multi-reader anti-collision algorithm based on time division multiplexing and high-Q algorithm. This algorithm introduces the schedule Q survey to achieve the global optimal effort, an FRA algorithm. The algorithm avoids reader-to-reader interferences and reader-to-tag interferences problems through centralized algorithm. Now I will introduce the DCS algorithm. The DCS algorithm is distributed color selection algorithm. It's a multi-reader anti-collision algorithm based on time division multiplexing. It's based on principle that in case of reader collision, the collision reader select time slot randomly to avoid collision. This algorithm needs a long time to complete the global optimism. Then I will introduce the high-Q algorithm. The algorithm introduces the schedule Q survey to achieve the global optimal effect. The Q-learn algorithm is invoked in Q survey to learn the relative collision information collected by the reader, and then the optimal collection scheme is made according to the learned result, so as to achieve the maximum number of readers working at the same time and the reader collision rate to a minimum. When the number of readers increases, a huge amount of collision information needs to be processed, which may affect the efficiency of the system. Finally, I will introduce the NFRA algorithm. The algorithm avoids reader-to-read interferences and reader-to-tag interferences problems through centralized algorithms. Survey broadcast an array command that contains a random number range. Readers generate their zero random number by receive EC. The survey then issues a sort command, and each reader compares the value in OC with its random number. If the numbers are equal, the reader issues a beacon to determine if a collision has occurred. After the beacon frame, they will send the frame to the adjacent readers. When readers don't detect any conflicts, by the way, NFRA can provide adjacent readers receive the next OC from the survey. The next OC is not identified due to all the adjacent readers that determine beacon conflicts are in the next EC. Now I will introduce the type of read collision. When multi-reader work at the same frequency as shown in figure 1, RE send the command first. T1 receive command from R1 and then responds to R1 after processing. At the same time, R2 also send the command. Since R1 is in interference range of R2, the command from R2 interferences with T1's command, and the first type of collision occurs. Then, as shown in figure, T1 is within the reader range of R1 and the interference range of R2. When reader R1 sends a command, R2 is also send a command. At tag T1, the command sent by R1 cannot be received normally due to the interferences of R2 command, resulting in the second type of collision. Now firstly, is the third type of collision. In this scenario of multi-reader working at different frequencies, as shown in figure, T1 is within the reader range of R1 and R2. When reader R1 sends the command, reader R2 is also sending the command. Two effective reader commands collide at tag T1, which cause T1 cannot receive the command normally. This is the third type of collision. Now we learn the third type of collision. Then I will introduce the grouping algorithm. For three types of reader collision, different measurements can be taken to avoid those collisions. Set the reader range are R1, R2, the interference range are I1, I2, and the distance between two readers to D, the first type, and the second type of collision are collectively called reader range and interference range collision. The last type of collision is called reader range and reader range collision. RIC will occur when D lower R1 at I2, so that reader with RIC can work at different frequency to avoid the collision. RIC will occur. RRC will occurs when D lower R1 at R2 equal to R1. The reader with RRC can avoid collision only when they work in different time slots. Now I will introduce the grouping algorithm. According to the analysis of reader collision, the algorithm uses the connected graphic filter to modify the interfaces between two readers. When the distance between two readers is less than 2 times reader, that is, when the RRC occurs, there must be RIC. In this algorithm, the concept of site is proposed. After RIC is completed, the number of colors need for line represent the number of sites. There is no RIC between readers in each site, and they can operate in the same time slot. There are still RIC between the readers in one site. That is, the distance between two readers is less than the sum of the reader range and the interferences range. Then the interferences graph is constructed again for each reader in the site and processed by vector color algorithm. The number of colors needed for line represents the number of groups in each site. There is no reader interferences between each group of readers. They can work at the same frequency and time slot, and different groups in the same site can work at different frequencies to avoid collision. This ensures that readers in the site can operate simultaneously with the minimum of channels. Then I will introduce the process of the algorithm, as shown in figure. In this algorithm, the polling survey broadcasts one or more message commands, named MC, to the readers. MC contains the address information of readers, the corresponding site and group information. After receiving MC, a reader will compare its own address information with received information to check if they are identical. If the result is identical, the reader will put the corresponding site and grouping information into itself. Otherwise, the reader will continue to wait. When all MC commands are set, the polling survey broadcasts the multi-start group command, named SJC, to readers. SJC contains the grouping label with operation grant, and the corresponding channel information has been assigned. The group labels contains in multi-SJC belong to a site. After receiving SJC, the reader compares the group label with its own group information. If they are equal, the channel information is received and waiting for the identification of the site information. If the two are not equal, the arrival of the next SJC is waiting. After multiple SJC are sent, the server runs and start site command, named SSC. SSC contains the site label that has been operating grant. After receiving the SSC, the reader that successfully matched the group information will compare the site information. If the comparison results are equal, it will start to identify attacks according to an allocated channel. If the comparison results are not equal, it will wait for the SJC command. Readers that failed to match group information will not answer after receiving SC. After waiting for the communication between a reader and tags, polling survey will send multiple SJC content groups labels and corresponding channel information. The rest of the process is similar to the previous process until all tags are identified. Now the simulation scenario. The simulation parameters are shown in Table 1. Now I will introduce the system the simulation result. As shown in figure. The simulation results compare the system efficiency of different algorithms when the number of readers increase from 100 to 1000 in destiny secondary. From the simulation results, we can see that when number of readers is less than 200, the system efficiency of the proposed MC-NCO is slightly lower than NFI and HiQ algorithm. When the number is greater than 200, the system efficiency of this algorithm is the highest. NFI algorithm and HiQ algorithm are lower than the proposed MC-NCO, and DCS algorithm is relatively low in the scenario. So, therefore, when the reader is fewer, the efficiency gain brought by grouping cannot offset the efficiency drop caused by frequency division, resulting in the efficiency will be lower than if I and HiQ algorithm. Then I will introduce the system efficiency in spare scenario. In this scenario, the number of readers increased from 10 to 100 in spare scenario. From the simulation result, we can see that when the number of readers is less than 30, the system efficiency of this algorithm is basically the same as NFI algorithm and HiQ algorithm. When number of readers is greater than 30, the system efficiency of this algorithm is the highest. NFI algorithm and HiQ algorithm are basically the same, but slightly lower than this algorithm. The efficiency of DCS algorithm is the lowest because in the spare scenario, the reader place can reduce the accuracy of the collision. Then I will introduce the field number.
of control command number letters. One control command cannot avoid reader collision. The control command is called field. This simulation result shows that the number of country command field of DCS algorithm is the most. The number of field command of HiQ is less. An FIA algorithm proposed MCNCO can completely avoid reader collision, so the number of field control command is 0. The simulation results in figure compare the system control efficiency of different algorithms. In this comparison algorithm, the control success rate of tag ADC is relatively low, and the success rate of HiQ algorithm using equivalent and relative adjustment is greatly improved. An FIA algorithm as a proposed MCNCO can successfully avoid all collisions through control command so that the control success rate is 100%. Conclusion. The algorithm uses polling survey to process the interferences graphic with vector. Calling algorithm in graphic theater to get read sites that can avoid interferences, and then using algorithm to process readers in each site to get multi-reader groups. There is no interferences between the readers in one group, which can achieve the same frequency and time slot operating without interferences. There are RAC among different groups in a site, and readers in different groups can work without interferences by running in different channels of the same time slot. The readers with interferences between different sites can only be avoided by running in different time slots. The maximum number of readers can work without interferences in the time slot by sending information to the readers through the polling survey. Compared with DCS algorithm, HiQ algorithm, and FIA algorithm, this algorithm groups readers by polling survey, avoiding the possible reader collisions. The simulation results show that proposed MCNCO is better than other algorithms in system identification and system contribution. Therefore, this algorithm can be applied to RFID real-world scenario, where readers are sparse and densely distributed. Now, thank you everyone.
Hello everyone. Now let me introduce the work we done in our paper, Cell Cooperation-Based Channel Access Mechanism for LAA and Wi-Fi Coexistence. My presentation will be divided into 5 parts, namely the research background, our contribution, protocol design, simulation settings and results, and finally the conclusion. Now, in the era of mobile internet advancement, the number of mobile devices is increasing rapidly. Mobile devices transmit a large amount of data through interconnection, and the traffic carried by cellular network systems is greatly increased, which makes wireless operators experience explosive data traffic growth. These bring a great challenge for operators to further enhance the capacity of mobile communication systems, satisfying the increasing demands of users. However, the licensed frequency spectrum resources are insufficient, which makes the service pressure of the licensed frequency band raised sharply, difficult to guarantee higher service quality. In response to the above phenomena, the research of deploying LTE network system in unlicensed frequency bands has become an important part to improve the performance of communication network. In 2014, the Third Generation Partnership Project launched the research project Licensed Assisted Access using LTE
LAA provides a feasible way for major operators to make reasonable use of unlicensed frequency band resources and help to improve the overall performances of mobile communication networks. Especially in areas with heavy service demands, wireless data services in LTE can be effectively offloaded to unlicensed spectrum resources, thereby improving the capacity of LTE operators. LAA is mainly deployed in 5 GHz unlicensed frequency band, which affects the operation of systems working on this band, especially the Wi-Fi system, and will increase the risk of data collision. Therefore, how to establish a suitable coexistence access mechanism is a significant research direction to help LAA system and the Wi-Fi system coexist fairly in the unlicensed frequency band. In order to minimize the interference to Wi-Fi system, listen before talk mechanism was introduced into the standard, hoping to realize the protection of Wi-Fi system under the influence of LAA, as well as guarantee the performance of LAA system. There are 4 types of LBT. The Category 4 LBT, which is also known as exponential backoff LBT, was the access scheme specified in Release 13 to help LAA share the channel resources with Wi-Fi as fair as possible. Since a large number of studies consider the relationship between Wi-Fi and LAA in the coexistence scenario from the contention aspect, and the performance improvement of one system and the whole scenario are achieved by sacrificing the performance of the other system. The cell cooperation-based channel access mechanism is proposed in our paper to make the 2 systems as fair as possible in channel access, as well as improve the efficiency of the coexistence scenario. Simulation results manifest that the proposed cell cooperation mechanism improves the communication performances of both LAA and Wi-Fi, as well as the spectrum efficiency in the coexistence scenarios with high channel resources demand. Let me first have a brief introduction to the exponential backoff LBT in LAA. The LBT access procedure includes 2 stages: initial clear channel assessment and extended clear channel assessment. The diagram for it is shown in the right figure. In ICCA stage, if channel is ideal within the deferred duration, the eNode B transmits data directly. Otherwise, it enters the ECCA stage. In ECCA stage, after the channel is ideal for a period of the deferred duration, the eNode B back off the access for a number of ideal time slots before transmission. The number of ideal time slots are defined at the backoff counter. The backoff counter is a randomly selected integer within the contention window. Firstly, the backoff counter is randomly selected in the domain from 0 to contention window mean. Then the backoff counter is decreased by 1 for every ideal time slot. When the backoff counter reaches 0, the device can access the channel and transmit. If 80% or more received HIRQ ACK in reference subframe are NACK, the contention window size goes to the next higher value. The allowed values for contention window are exponential sub 2. The diagram and the adjustment in exponential backoff LBT are quite similar to that of Wi-Fi system to provide coexistence fairness. The basic idea of the proposed cell cooperation-based channel access mechanism is to establish cooperative cells with LAA and Wi-Fi on the premise that LAA and Wi-Fi devices can understand the signal from each other. An LAA ENB and a Wi-Fi AP form a pair of cooperative relationship. During the transmission of LAA ENB, it notifies the shared transmission opportunity to the paired Wi-Fi AP. Then the Wi-Fi AP can access the channel directly after the transmission of ENB finished, and vice versa. Let's look into the details. The figure shows the diagram of the condition that the LAA transmits first and the Wi-Fi gets the shared transmission opportunity. During the channel access and transmission of the LAA ENB, the LAA ENB notifies the paired Wi-Fi AP to share the transmission opportunity with the information piggybacked in the header of the transmitted frame. Then the AP received the information needs to update its network allocation vector with time duration equal to the transmission time of the ongoing LAA frame. After the LAA ENB completes the transmission, the paired Wi-Fi AP can access the channel and transmit data right after the channel is ideal for short inter-frame space. No longer need to perform backoff again. The utilization of the shared transmission opportunity is shown within the blue circle. Similar channel access mechanism for LAA ENB in cooperative relationship if an AP transmits first. It should be noticed that this cooperative relationship should be finished after the cooperation completes, and then the two cells need to compete for the channel resources again if they have data to send. After one of them successfully accesses the channel, they can cooperate again. Otherwise, this pair of devices may occupy the channel resources all the time if they always have data to send. In the simulation, we ran two downlink coexistence scenarios to test the cell cooperation mechanism. Two operators are deployed in the scenarios. Operator A is for LAA system and operator B is for Wi-Fi system. In scenario 1, the two operators are deployed in a 10 times 10 square meter square, which is separated by a distance of 10 meters. In scenario 2, the two systems are mixed in a 30 times 30 square meters area. Each operator has 10 cells and each cell has 5 user devices. So there are total 8 cooperative pairs and 16 nodes need to transmit. And there are some parameters setting. In simulation, we use the category 4 LBT with priority 3 for LAA and Sigma CA with best effort service for Wi-Fi. And we fixed the physical layer data rate to 9.9 megabits per second. Apart from the cell cooperation mechanism, the carrier sending threshold of Wi-Fi is also a variable in our simulation. The figures below show the scenario's total throughput comparison of scenarios implement or not implement the cell cooperation mechanism. The total throughput is the throughput of LAA system plus the throughput of Wi-Fi system. Checking the legend, the above 3 lines in the two figures are the results with cell cooperation implemented. The total throughput of the coexistence is raised more than 1 megabit per second in average and almost reaches the maximum data rate allowed in the parameter setting. The maximum data rate, is 9.9 megabits per second in the setting. These figures show the throughput and average time delay per packet for the two operators in scenario 1 with Wi-Fi carrier sensing threshold of -82 dBm. Due to the cell cooperation mechanism, the performance of Wi-Fi is greatly improved, especially when Wi-Fi is in a more conservative state. At the same time, LA performance also gets a little improved, which means that the coexistence scenario has higher spectrum efficiency, and this is not achieved by sacrificing one of its systems. The simulation is also conducted in scenario 1 with a larger operator distance under the condition of a -62 dBm Wi-Fi carrier sensing threshold to evaluate the effectiveness of the proposed cell cooperation scheme when the mutual influence between the two operators is not severe. However, simulation results show that the throughput improvement effect of the proposed scheme reduces when the distance between two operators increases, which means the proposed scheme can better reveal its advantages in the coexistence scenarios with higher traffic density and more channel access demands. And it is not necessary to be implemented to promote the spectrum efficiency in non-hotspot areas. In this paper, we propose a cell cooperation-based channel access mechanism, treating LAA and Wi-Fi systems from the collaborative perspective, making an LAA cell and a Wi-Fi cell in the coexistence scenario form a pair of cooperative relationship. Simulation results show that the proposed cell cooperation mechanism can improve the throughput and time delay performances of the Wi-Fi system, as well as the entire system of the coexistence scenario with a high channel resources demand. That's all for my introduction to our paper, the Cell Cooperation-Based Channel Access Mechanism for LAA and Wi-Fi Coexistence Scenario. Thanks for your watching.
Okay, my name is Fen Zhaotun. I come from Shanxi Xi'an, studying at Cheng'an University. I'm honored to attend this conference. Next, I will introduce my paper and related research. My paper title is Dynamic Time Slot Adjustment Based Beamform Trimming for the Next Generation Millimeter Wave WLAN. Please refer to the outline of the presentation. First, I will introduce the research background of this paper, and then I will introduce some contribution of this article. I will focus on this part of the practical design and use the simulation results for further explanation. Finally, I will make a conclusion of this research. With the widespread use of WLAN, the unless spectrum in the low frequency band has been close to saturation. Therefore, the most commonly used 802.11 WLAN, such as 802.11n, 802.11 AC, cannot meet the constantly updated wireless. The data rate of the application. In order to provide the user with a higher data transmission rate to meet the constantly updated data transmission requirements, in order to adapt to more complex net deployment scenarios. More usable spectra and more cutting-edge technology are required. Millimeter wave has more listenable spectra, which can provide more opportunities for emerging broadband application. Currently, millimeter wave communication has been paid to the 5th generation mobile communication system and some cutting-edge wireless communication system. Among this abundant laser spectra, both academic and industry suggest that the 60 GHz unlicensed MIMO wave frequency band should be given publishing. IEEE 802.11 AD uses the 60 GHz frequency band. In the previous work, we have intensively evaluated the performance of IEEE 802.11 AD. But there are still many problems to be solved under the high design network deployment in the future. Because millimeter wave propagation suffers from several path loss and signal attenuation, it is almost impossible to achieve long latency communication transmission when using traditional directional communication. Therefore, beamforming technology that can concentrate the transmit power and the receiving around on the narrow beam, commonly used for directional transmission, and beamform trimming (BFT) is the key process to realize directional communications. Therefore, the BFT process must be carefully designed in the practical, and the best transmission sector must be determined to the full property for direction transmission. If the process of establishing directional communication transmission take too much time, the communication delay will be too long. Quality of the experience is reduced. However, because the BFT progress in 802.11 AD cannot be flexible configurations according to the different requirements, that makes the BFT progress very time-consuming and inefficient in communication. Therefore, it is very important to design a simple and effective BFT method, especially for WLAN that aim to reduce cost and complexity to provide high-quality service. The association beamforming training (EBFT) stage is akin to kernel access and BFT, because in high design user deployment scenarios, the number of nodes cannot continue to increase or change generally, causing nodes to crowded or not optimized when they enter a flank neighbor on time slot. Once the station cannot complete the beam chain in the ABFT, it will not be allocated to the time slot to complete the data transmission, but will wait for another ABFT in next beacon interval (BI) to access the training again, which will seriously affect QoE. In recent years, people have put forward higher and higher requirements for high-speed communication with a local area. Millimeter wave WLAN has attracted much attention for academic and industry, virtue of its ultra-large bandwidth and short range coverage. Beam trimming is a key technology on millimeter wave WLAN. The quality of beam trimming is related to communication performance and even communication. However, as the number of nodes continue to increase, the beam trimming efficiency of the traditional millimeter wave WLAN is very low, which affects system performance. This paper proposed a beamform trimming method based on the dynamic time zone adjustment for the next generation millimeter wave WLAN. The beam trimming slot in the spectral beam interval can be adjusted according to the complement of the beam trimming in the frequency PA. They are very important to the improving the efficiency of beam trimming. The simulation results from the method proposed in the paper can effectively improve the beam trimming efficiency and has a small impact on the performance of the system. In the future high-end deployment scenario, high requirements are put forward for the beamform trimming of node in the cell. In this part, I will introduce some design of this paper for the practical. We all know the beamform training progress of the IEEE 802.11ad or AY protocol is normally performed with a beacon interval. BI is divided into BHA and DHA. In the BHA, beam trimming to get the best beam from the communications. BHA is divided in three parts: BTA, ABFT, ATI. BTA is a beacon transmission interval, and association beamforming trimming, and announcement transmission interval. In the DTA is divided into SP or CPAP. This is a beacon interval frame structure. In the ABFT frame, first there is a certain count of ABFT slot for station to choose to complete beamform trimming. The ABFT is a log code in HBI, and a certain amount of ABFT slot are set in the ABFT phrase. Before the beam trimming starts, that is, after the node receives the DMG beacon frame in the ABFT, the AP receives the SSW frame set by station routing every sector directionally. Based on the received SSW frame, the AP determined the station. AP determined the station with the strongest transmission energy to set the sector and sector information. It is stored in the sector sweeps feedback frame. It means SSW feedback frame, and returned to the station. This process completes the beamforming chain of the station transmission sector. In the ABFT frame, the station in a cell randomly select the training time slot, which will cause several stations to select the same time slot and cannot complete the training. When the number of the nodes in the cell increased, multiple nodes might choose the similar ABFT time slot, causing beamform training conclusion. For example, this picture, when the station 3 and station 5 enter the same time slot, we cannot complete the beamform training from both nodes at the same time. The motivation of this paper is to solve the problem of training conflict. and the decrease of beamforming training efficiency. Due to the increase of the number of nodes during beamform training, the beamform training method in the APFT phase of the counter 802.11 AD practical is not flexible enough because it is usually necessary to set up enough APFT slots in advance to cope with the nodes in a cell. Such a setting cannot meet future high-density network deployment scenarios as the number of nodes in a cell increase. More and more stations will enable in the beamform training phase. Conflicts are generated and training cannot successfully complete and thus cannot be solved, which reduces the training efficiency of the entire APFT phase. Here are key ideas of this paper. Dynamically adjust the number of the APFT slots according to the number of nodes that have been training complete at this stage to meet the training nodes of all nodes in a cell. Use link maintenance function to ensure node communication quality. Adjust the sector rotation rate to half of the original rate to reduce other overhead. This picture is a MAC layer frame sketcher. We can see that the APFT slot here is not flexible, but not fixed, and the number of SSW frame is only half of the number of sector. It will not conflict occur in the APFT frame of NBI. The number of APFT slots is dynamically adjusted according to the complete situation. In the next BI, the nodes that have not completed the training will be treated first in the next BI. After the beamforming training is complete, the training can be restarted only after the communication quality of the node link decreases. This picture describes the frame structure change in the two BIs before and after the training complete. At the beginning, only 4 time slots can provide to training, but there are 6 more nodes to be trained in a cell. Obviously, the training of up to 4 nodes is affected. Therefore, in the following BA's number of APFT slots is adjusted first, and then the conflict nodes are trained first. It means station 3, station 4, station 5, station 6 will be first trained in the APFT. And station 1 or station 2, when the communication quality drops and the node access training again. The rotation rate when training the best setting sector can be reduced to half of the original according to the best receiver sector of station. Look at this picture. Station only rated 108 range with the best receiving sector at the center and set SSW frame. We use the configuration interquery i7-8750H main frequency, 8G-bit memory, and 64-bit Windows 10 operation system. All codes are developed under the NSC simulation platform. The simulation configuration is a single cell scenario with 1 AP and 6 stations in the cell. Create station condition by reduce the number of the past APFT slots to simulation higher than network deployment scenarios. The simulation configuration is derived according to the height and deployment scenarios, and their configurations shown in the table 1. According to the system throughput and packet slot rate, the simulation compares the spread of any dynamic time slot adjustment method at the link distance machine with the original practical spread. And shown in the figure, the blue slot line represents the original script without added functions, and the yellow, the node line, indicate the spread with the dynamic time slot method added, and the red dot line indicate the script with the dynamic time slot adjustment at the link distance machine ended. The simulation results show that from the throughput group, the performance of the group with only dynamic time slot adjusted is more, and the link distance function can be better compensated. From the drop date rate history, the packet load rate with only dynamic time slot adjusted is here, and the packet loss is merely considered in the first few BI. This situation is caused by the failure of a previous training conflict. This paper provides a beam training method for the next generation millimeter wave WLAN based on dynamic time slot adjustment. In order to adopt to change in the number of nodes in the cell and reduce beam trimming conflict caused by changing the number of nodes, the original fixed number of ABFT are set to a form that can be dynamic adjusted according to the beam trimming conflict. The IEEE 802.11ad OAY beam trimming shaped by the dynamic adjustment of time slot is proposed in order to adapt to change in the number of nodes in a cell and reduce beam trimming conflicts caused by change in the number of nodes. The original fixed number of ABFT slot is set to a form that can be dynamically adjusted according to the beamform trimming conflicts. The simulation results show the design practical improve the efficiency of beam trimming while ensuring the reliability of the system, can better adapt to future high design network deployment. Okay, thank you.
Hello everyone. It's my great honor to deliver my presentation today. Today my topic is power control-based spatial reuse for LAA and Wi-Fi coexistence. My presentation is organized as follows. Firstly, I'm going to offer some backgrounds of licensed assisted access. Secondly, I will show the contribution of this paper. Then I'd like to go deeper into the protocol design of the proposed scheme, and as well as the simulation results. Finally, I will make a short summary. My presentation will take about 15 minutes. With the rapid increase in the number of mobile users and the diversification of mobile service requirements, a rising demand on network capacity is generated, which promotes the rapid development of the fifth-generation mobile communication system. Due to the scarcity of spectrum resources of the conventional licensed band, the unlicensed frequency band has raised public awareness in recent years. In September 2014, 3GPP launched the research project of licensed assisted access using LTE. The target of this project of LAA is to design a single global solution framework and protocol to ensure the efficient operation of LAA on unlicensed band. In 2017, 3GPP Release 16 established the project group for 5G new radio in unlicensed spectrum, introducing LAA technology into the 5G networks. There are some facts, however, restrict the application of cellular networks on unlicensed band. Apart from some regional regulations, a large number of wireless systems and protocols, such as Wi-Fi, Bluetooth, and Zigbee, have already been operating on unlicensed band, among which the most significant one is the Wi-Fi system. Therefore, the deployment of LAA has to consider the fair coexistence with the existing Wi-Fi system. According to 3GPP TR 36.889, the impact of an LAA network to Wi-Fi networks shall not be more than that of an additional Wi-Fi network to the existing Wi-Fi services concerning throughput and latency. The present coexistence scheme used in EAI is the listen before talk scheme. Here I would like to provide the downlink channel access procedure of EAI based on this scheme, the flowchart of which is shown on the right of this slide. An EAI node B goes to ICCA, short for Initial Clear Channel Assessment stage, before the first transmission, and loops in ECCA, Extended Clear Channel Assessment stage otherwise. During ECCA stage, EAI transmissions are performed after the channel is sensed to be idle during a deferred duration of TD, and after the counter N is decremented to 0. This paper has made the following contributions. In this paper, we propose a power control-based spatial reuse, or the PC-based SR scheme, for EAI and Wi-Fi coexistence. And the simulation results demonstrate that the proposed scheme improves the performance of both EAI and Wi-Fi and enhances the fairness with respect to throughput and latency. Many works have been done in recent years aiming to increase the system performances of EAI or of Wi-Fi with different KPIs. However, how to improve the performance of both EAI network and Wi-Fi network in coexisting scenarios remains a difficult problem. Our proposed scheme of power control-based spatial reuse aims to increase the probability of concurrent transmissions, and thus to increase the performance of EAI and Wi-Fi in coexisting scenarios. Now, let's go forward to our protocol design. We assume that EAI and Wi-Fi networks are able to recognize the signal of each other. A new parameter of maximum energy detection threshold is added apart from the normal energy detection threshold. An EAI node should raise its energy detection threshold after recognizing Wi-Fi signals and transmit with adjusted power, and vice versa. The transmit power adjustment shall follow the equation as is shown on this slide. This transmit power adjustment allows more nodes to transmit packets at the same time without collisions. Here we also use a TPC tag for fairness insurance. That is, when a node is transmitted with a lowered power, it shall let other nodes nearby know, and nodes with packets to transmit shall compete to access the channel at the same time after current transmissions. Otherwise, it is possible for one node to always transmit with a lowered power, as is shown on these two pictures. This flowchart of the procedure of downlink transmissions using the proposed scheme is provided on this slide. As is mentioned before, if an EAI base station recognizes the signal from Wi-Fi nodes, and the energy detected is between the two thresholds, the channel is declared to be idle and transmissions shall be performed with a lowered transmit power. Otherwise, the transmit power remains the same, and the channel state is determined based on the normal energy detection threshold. This power control procedure is the same for Wi-Fi networks. If a Wi-Fi base station recognizes the signal from EAI nodes and the energy detected is between Wi-Fi's two thresholds. The channel is declared to be idle and transmissions shall be performed with a lowered transmit power. Otherwise, the transmit power remains the same and the channel state is determined based on Wi-Fi's normal energy detection threshold. This slide shows the basic scenario used in this paper. It consists of an EAI cell and a Wi-Fi cell, and the distance between the two cells is d in meters. Table 1 shows the energy detection thresholds of this scenario. It has three kinds of configurations, and the first configuration is the traditional configuration suggested by 3GPP, and the second configuration is used for comparisons, and the last configuration is the proposed configuration with the PC-based SR scheme. Table 2 shows other parameters used in these scenarios. They are about scenario parameters and application layer configurations, and also about specific parameters for EAI and Wi-Fi networks. This paper makes simulations on the three scenarios. Now I'm going to show you some of the simulation results. First, this scenario aims to make performance comparisons between different distances between base stations. Here, the distance between the two cells is between 15 meters to 40 meters, and each cell has 10 users. It can be seen that both systems achieve performance improvements using the proposed scheme. In the second scenario, we fix the distance to be 25 meters. Here we change the UDP rate, and each cell still has 10 users. This figure shows that both EAI and Wi-Fi are improved in throughput and latency, the saturation throughput of which grew by 20.3% and 102.3% respectively. That's enhancing the fairness to Wi-Fi networks in coexisting scenario. Table 3 lists the average saturation throughput per user of EAI cell, Wi-Fi cell, and on average. In the third scenario, we fix the distance to be 30 meters. Again, we change the UDP rate, and each cell still has 10 users. And here these figures show that both EAI and Wi-Fi are improved in throughput and latency, the saturation throughputs of which grow by 36.5% and 20.3% respectively. Table 4 lists the average saturation throughput per user of an EAI cell, the Wi-Fi cell, and on average. Apart from that, the number of users per cell indicates the level of traffic inside a cell. With a certain amount of the total resources, the more users in a cell, the less resources can be allocated to each user, indicating the higher density of the cell and leading to a lower average saturation throughput of each user. Therefore, we changed the number of users per cell in the last two scenarios. The consequence is that the system performance is improved regardless of the tested service densities, as is shown in these 4 pictures. The left 2 figures is about the total system saturation throughput, and the right 2 figures is about the saturation throughput of LAA and Wi-Fi respectively. Finally, I'm going to make a short summary of my presentation today. In conclusion, in this paper, we propose a power control-based spatial reuse scheme, which increases the probability of concurrent transmissions in LAA and Wi-Fi coexisting scenarios. Combined with the simulation results and analysis in the previous several sections, it can be considered that our proposal enhances system performance and fairness with respect to throughput and latency. And this kind of enhancement is to both LAA networks and Wi-Fi networks. That's all for my today's presentation. Thank you so much for your listening.
Hello everyone, welcome to my presentation. My name is Gan Nortin, a master student from Northwestern Polytechnic University. My major is Information and Communication Engineering. It is a great honor to have this opportunity to join this conference. The subject of my presentation is low-latency guarantee protect based on multi-links scheduling random access in the next generation WLAN. IEEE 802.11be, as shown in this picture. The main part is the low-latency guarantee. My speech is divided into 5 parts. First, some introduction about the next generation wireless local area network. Second, what do we manually do? Contribution. Third, the design ideas based on this protect. Fourth, design the simulation scenario verifies the protect we designed and give some explanation. The last part is conclusion. The first part, introduction. With the rapid development of mobile internet and the widespread use of smart terminals, the amount of data carried by wireless network has continued to increase sharply, and wireless servers have gradually become diversified. The requirement for low-latency guarantee of wireless network and the improvement of network throughput is immediately. In the next few years, video traffic will become the main data traffic type, such as 4K and 8K video, and with the emergence of more advanced technologies, its throughput demand will continue to grow to tens of GPS. At the same time, new applications requiring high throughput and low latency are also proliferating, such as augmented reality, virtual reality, giant games, and remote official and so on. The IEEE 802.11 will have to further improve Wi-Fi to meet the needs of these specific scenarios with high throughput, low latency, and high reliability. Second part, contribution. This paper proposed no delay guarantee algorithm based on multi-link scheduling random access. The AP perform effective coordinated scheduling on multiple links according to the current channel condition. It not only reduces network transmission delay but also improves network performance. The simulation result, the low-latency guarantee protect based on multi-links scheduling redundancies improves the delay performance will improve throughput and reduce delay. Part 3. Protect design. This part will mainly introduce the related knowledge of the next generation WLAN 802.11b, the multi-link operation. Based on this, we propose this algorithm and give a detailed process in this section. 1802.11b all formed in May 2018 to form the EAI topic interest group, which is determined to enable a new MAC and physical NAIL operation model which can support the maximum throughput at least 13 Gbps. The GHT study group was launched in July 2018 with the primary goal of forming an effective development process. At the IEEE 802.11 standard working group meeting held in March 2019, the project author of the next generation WLAN standard EAI working group all discussed and reversed, and the project all named 802.11b. In May 2019, the next generation WLAN standard officially entered the working group stage from the study group. It is expected that the 1802.11b standard will be launched around 2024. In production version of IEEE 802.11, only one link or used B12 an AP and a station, and worked on one frequency band, such as 2.4 GHz, 5 GHz, to achieve the technical goal of extremely high throughput. IEEE 802.11b introduced multi-link operation. IEEE 802.11b allows the device to have multiple states of ratio and work in multiple frequency bands, such as 2.4 GHz, 5 GHz, 6 GHz at the same time. As shown in this figure, an AP multi-link device is naked the role of the traditional AP, and the non-AP multi-link device is naked the role of the traditional station. There is a big difference in concept. An AP multi-link device can have multiple APs working in different frequency bands, such as AP1, AP2, and AP3 until APN in this figure. But these APs are in the same device, and so as the station multi-link device, where in AP1, AP2, and AP3 work in different frequency band, but AP1 and stay 1, AP2 and stay 2, AP3 and stay 3 work in the same frequency band. The link formed by them are called link 1, link 2, and link 3. Therefore, a link corresponds to connection of APs and states working in the same frequency band. It can be seen from the figure that different links can work at the same time. For example, the transmission of frame 1 on link 1 in the figure fails, and the AP multi-link device chooses to retransmit the frame on link 3. It can be seen that multi-link operation enables APs and states to have a more bandwidth resource, thereby laying an important foundation for achieving the goals of EHT. In addition, efficiency coordination between different links can further improve the efficiency of access, transmission, and retransmission. Regarding how to ensure low-latency transmission in wireless networks, this paper proposes a low-latency guarantee protocol based on multi-link scheduling and random access. On Figure 1, we can know Figure 8. High priority servers have been transmitting data on a certain link, and the rate of generating data packets increase because high priority servers enter the channel more aggressively. When we regularly send TSF frame on each link, we can know it can reduce the transmission delay of high priority servers and reduce the probability of conflicts between high priority servers. We can know that this protocol not only improves the throughput of the network and reduce the transmission delay of the network, but also reduce the packet loss rate of the internetwork. In order to effectively protect the low latency data transmission in the next generation timeline, this paper proposes a scheduling random access protocol based on multi-links. The spatial agreement process can be divided into the following steps. Step 1. AP periodically send a traffic scheduling announcement frame on each link, and when station performs data transmission on the link assigned to the specific servers according to the TSF, the destination node will return an acknowledgement on that link after receiving data. Step 4. In each TSF cycle, each node transmits a specific service on the specific link according to the information sent by the TSF frame. In order to enable the AP to effectively schedule reliable link results to transmit high priority servers, we have designed a scheduling algorithm based on servers priority difference. Step 1. When the high priority servers is ready to enter the queue, compare the utilization rate of each link and the number of high priority servers in the queue. When the high priority servers in a link queue are significantly lower than the average value of the high priority servers in all link queues. When high priority servers are more evenly distributed in the queue of each link, we judge which link queue the high priority servers enter according to the utilization rate of each link. When the channel utilization of a link is significantly lower than the utilization of other link, high priority servers will enter the link queue. When the channel utilization rate of all links are basically equal, high priority servers will random select a link and enter its queue for backhaul. The frame structure of TSF is extended according to the frame smart of the 802.11 traditional tracker frame, as shown in this figure. Also add a link info field in this TSF to indicate the link number, server traffic type, and the transmission duration in the link. The other fields are consistent with the traditional tracker frame structure. Part 4. Simulation result. How to gating delay has become an important research direction in the next generation WLAN. So, what is the effect of the delay gating protocol based on this random access method of scheduling multi-link designed in this paper? Based on this, we designed and implemented algorithm on this N3 simulation platform and designed specific scenario to verify or protect. Simulation 1. Based on this platform, it also has realized the test and verification of the delay gating of this protocol and the traditional single link. First, we designed a basic single cell scenario to verify the performance of this protocol and the traditional single link to compare all aspects. The specific parameters of this sense as shown in this figure: number of IP1, number of state 1, the downlink, and the number of link for multi-link is 2, single link is 1. We can know that the purpose of this simulation is to compare the basic network performance of this protocol with the traditional single link, mainly from the network throughput and the service transmission delay. And showing this figure, we can clearly feel that compared to the traditional single link model, the multi-link scheduling protocol only provides the support of the inter-network, but also reduce the transmission delay of this inter-network. We can also design a single cell transmission scenario to verify whether the scheduling protocol can effectively reduce the transmission delay of high priority traffic and improve network performance. The basic parameters of resistance showing this number of IP is 1, the number of station is 4, data rate from 0.1 to up to 500. The number of link is 2. The difference of the calculation is scheduling algorithm. From this figure, we can see that the scheduling algorithm can effectively guarantee the high priority transmission delay for this part, and the data rate increased. The function of the scheduling protocol become more apparent, and also can improve the throughput of the inter-network. The next part, conclusion. For the simulation result, we can see that compared with the traditional single link, this protocol can not only effectively improve the throughput of the inter-network, but also reduce the traffic transmission delay. The scheduling protocol improves the communication quality of the inter-network in the case of multi-links. And the low-latency gating protocol based on multi-link scheduling random access in the next generation WLAN IEEE 802.11b is proposed, and we can know that its protocol can not only effectively improve the throughput of the internet network, but also reduce the service transmission delay. And that's all my presentation. Thank you.
Hello everyone, it's time to begin my presentation. The presentation will be divided into 5 parts, which is background, contribution, dynamic priority adjustment scheme, simulation, results, and conclusion. With the popularization of wireless network and the rapid growth of global user business, wireless local area network, that is WLAN, has become one of the most important data service carriers. However, as the number and demand of users increases, the performance of requirements for business transmission are also steadily increasing. In order to meet the increasing user demand, both academic and industrial circles are paying attention to the key technology research and standardization of next generation WLAN. With the rapid development of IEEE 802.11 WLAN, the user's demand for quality of service, that is QoS, is increasing. As the diversity of service types and the number of delay-sensitive services increased, it is necessary for network transmission to keep pace with the times and provide corresponding QoS guarantees for various services. Therefore, the improvement of QoS becomes the direction that the device business or the terminal mobile device is striving to improve. In 2005, IEEE 802.11e proposed a hybrid coordination function based on the distributed coordination function and point coordination function in the original IEEE 802.11 protocol, which included enhanced distributed channel access, that is EDC mechanism. EDC can provide business priority service and provide QoS guarantee to some extent. However, the EDC mechanism has its limitations. Although it divides the business into 4 types and adds priority levels, but as new low delay business rises, its disadvantages are gradually exposed. At present, such network service as online game, VR, and automatic drive, which have very high request to the low delay, are gradually to increase. The demand for such service is growing fast, but for this drive the delay-sensitive services, the existing mechanisms cannot meet their transmission performance requirements, and there is no guarantee that they will complete the transmission within the specified time. Clearly, the EDC doesn't provide sufficient protection for delay-sensitive services. The next generation WLAN protocol, IEEE 802.11be, has taken low-latency guarantee as a key technology target, aimed at solving the problem of low-latency service in the EDC mechanism of IEEE 802.11e. Based on the analysis of the EDC mechanism of IEEE 802.11e, this paper proposed a dynamic access priority adjustment strategy for protecting delay-sensitive services. In this scheme, the delay-sensitive service packets are analyzed, and the priority of the service and the transmission scheme are dynamically adjusted according to the time threshold of the waiting time. Finally, the delay-sensitive service transmission requirement is guaranteed. The simulation results show that the priority dynamic adjustment model proposed in this paper is superior to the traditional EDC in throughput and the delay performance for the new delay-sensitive service. In IEEE 802.11, the DCF mechanism adopts contention access mode, which cannot provide accurate delay and bandwidth guarantee, so the DCF cannot guarantee QoS at all. IEEE 802.11e is a QoS enhancement to the MAC protocol in the IEEE 802.11, where ADC provides different levels of priority services. Figure 1 shows the basic queuing access method for ADC. The ADC mechanism introduces the concept of service queuing, which maps the service into 4 access categories. These 4 access categories are prioritized from top to bottom: voice, that is ACVO; video, that is ACVI; data, that is ACBE; background flow, that is ACBK. 4 access categories were divided into add priority. The EDC mechanism maps the service into 4 access categories, which were divided into add priority. That is shown in Table 1. In IEEE 802.11e, different levels of priority correspond to different channel intervention parameters. Channel intervention parameters include arbitration frame intervals, that is AIFS, and contention windows, including CWMax and CWMin. Different types of traffic have different priorities, so they can be transmitted according to different channel parameters and guarantee the QoS. In this way, ADC provides a degree of QoS assurance to the business. But the EDC is insufficient for low latency service. With the development of network services with high requirements for low transmission delay have gradually become the mainstream, such as online games, industrial control, VR, autopilot, and so on. These services in the transmission must be very low delay to meet users' needs. The question arises, for these low latency services, how should they be prioritized for transmission using traditional EDC mechanisms? We assume a simple scenario. During the transmission of an EDC, the channel is a relatively saturated state. At this point, there is a delay-sensitive packet queuing for queuing to be sent, as shown in Figure 2 below. To meet the needs of delay-sensitive business, it seems the easiest way is to configure all these business to be high priority, such as VO. If all the delay-sensitive services are treated as high priority services, the requirements of these services are guaranteed to some extent, but this will have a significant impact on the existing high priority services in the VO queue. As a result, the queue of high priority traffic is congested, which seriously affects the transmission quality. Obviously, this will have a bad effect on the transmission, so it's not a viable strategy. If the delay-sensitive business is all set to low priority, such as BE, that doesn't work either. While this approach protects the transmission quality of traditional high-priority services, the problem of delay-sensitive services has not been solved at all. Low-priority queues, which are inherently inefficient, will only become more crowded and will certainly not meet the needs of delay-sensitive services. The above analysis is only a simple case. We can see that the EDC mechanism has been unable to meet the transmission needs of a single delay-sensitive business. As a matter of fact, with the rise of delay-sensitive business is becoming more and more differentiated. Today, latency is no longer exclusive to certain packets. Packets of different services may have low latency demand. The only difference is the degree of the demand. For example, an ACBE type packet does not require much delay when entering the queue, but it cannot compete with the channel for a long time and cannot send. Then its delay will become more and more sensitive. That eventually causes the packet to fail. It is obvious that in reality, when more and more packets require delay, the traditional EDC will only fail more and more. A simple high-low priority configuration will only result in more and more serious errors. clearly not meet the needs of users. In this paper, a low delay guarantee strategy based on dynamic priority adjustment is proposed to provide dynamic priority adjustment for delay-sensitive services, so as to guarantee the emerging delay-sensitive services without affecting the transmission quality of the traditional fault services as much as possible. In order to simplify the analysis, high priority VO and low priority BE are set. The high priority VO and low priority BE are connected to a single channel in the ADC area. Within the node, VO and BE are divided into two queues, which perform queuing and retreating access independently. Suppose that packets of delay-sensitive service need to be sent. In order to meet the needs of users, there is a time t as the deadline for dispatching. That is, after such packets are queued for sending, they must be dispatched within time t. Otherwise, the packets will be lost. Assuming that after a packet is queued, its waiting time in the queue is recorded from 0 at t. It is obviously that the packet is sent at t less than t, according to business requirements. The implementation process is shown in Figure 3 below. First of all, in order to save channel resources as much as possible, when the delay-sensitive class packet just arrived, it was queued according to the traditional ADC idea, placed in the low priority BE queue to wait for sending, and then executed the backhaul according to the channel access parameters of the low priority service to wait for sending. It is best if the delay-sensitive packets are sent successfully in the BE queue. More often than not, the waiting time is near the deadline for sending, but there are still many packets in the queue ahead of delay-sensitive packets. If we don't act now, the delay-sensitive packets will not be sent in time. Through many experiments, the parameter alpha 0 is less than alpha and alpha is less than 1. Alpha is chosen as the threshold of waiting time of delay-sensitive packets in the low priority queue. That is, when t arrives alpha t. When t arrives alpha t, if the delay-sensitive packet is still not sent in the BE queue, it is urgent. To ensure the demand of service transmission, dynamic adjustment should be taken. At this point, the channel access parameters of delay-sensitive packets are changed from BE queue to high priority VO queue, which increases the possibility of receiving the packet's delivery services. When the delay-sensitive packets enter the high priority VO queue, it is best if the packets can be sent smoothly, but if the waiting time t is very close to the deadline t, and at this point the delay-sensitive packets are still queued in the VO queue, which makes it more urgent. Through many experiments, the parameter beta is chosen. Beta alpha is less than beta and beta is less than 1. Beta is chosen as the threshold of the waiting time of delay-sensitive packets in the high priority queue. That is, when t reaches beta t, if the delay-sensitive packet is still waiting to be sent in VO queue, it is more urgent. To ensure the service transmission requirements, dynamic adjustment measures should be taken again. The packet will be transferred to the head of the queue directly, and the low MCS is used for transmission to ensure that the delay-sensitive packets are sent before the deadline time to make the transmission more reliable. The entire delay-sensitive business dynamic assurance process is shown in Figure 4. So this process, the channel and the slot resources can be utilized to a greater extent, and the transmission quality of the original 4 types of services can be guaranteed to guarantee the performance of the emerging low delay demand services. This strategy is undoubtedly more applicable now and in the future. when low latency becomes the mainstream of network service. In order to meet the requirements of the experiment, we designed the simulation just as shown in this PPT. The EDC model is simulated on the S3 platform, and 3 kinds of services are generated at the same time. One is VO, the other is BE, and the other is low delay. Put them into the model to carry out simulation experiments. The design of the experiment is UDP transmission. The performance of the delay and the change of the throughput of the 2 processing methods are collected respectively. Finally, the advantages and disadvantages of the 2 methods are compared and analyzed. The 2 methods is the traditional EDC mechanism and the low delay dynamic adjustment scheme rather in this paper. Parameter settings are shown in Table 2. In the simulation of the low delay guarantee strategy with dynamically adjusted priority, the last contract period T of the low delay service is set to 10 milliseconds. Through a large number of experiments, the optimal effect is selected so that the configuration parameters alpha is equal to 0.5 and beta is equal to 0.92. That is before 5 milliseconds. Services with low latency requirements were transmitted as BE. After 5 milliseconds, is transmitted as VO. Transmission should be completed by 9.2 milliseconds as the latest. Using 2 different processing methods when the packet rate is different. The transmission delay of the low delay service are shown in Figure 5. The red one is the traditional EDC. The blue one is the dynamic adjustment scheme. Using 2 different process methods, the total throughput of network changes of different packet rates are shown in the following 6. The results of the experiments were analyzed and compared. The results show that, compared with the traditional EDC mechanism, the low delay guarantee strategy proposed in this paper can effectively guarantee the low delay demand of service within a certain limit. As we can see from Figure 5, when the packet rate is less than 130 Mbps, the traditional EDC can't provide the delay guarantee for the low delay traffic. The model proposed in this paper guarantees the data packets of low delay traffic can be sent at 9.2 milliseconds. When the throughput rate is higher than 130 Mbps, the low latency guarantee performance is affected due to the traffic increasing and exceeding the load carrying capacity. But it still performs better than the traditional EDC. As we can see from the Figure 6, the throughput of the proposed scheme is higher than that of the traditional EDC when the packet rate is higher than 39.5 Mbps. This is due to the low delay dynamic adjustment strategy proposed in this paper, which can make use of both low priority BE and high priority VO. Therefore, the total throughput and the transmission efficiency of the network are improved to a certain extent. It is concluded that the dynamic priority adjustment model in this paper is effective not only for low delay traffic but also for network throughput efficiency. According to the simulation that the low delay guarantee strategy based on EDC and can provide more protection for the emerging low delay services than the traditional EDC. In the face of the booming low delay species, the traditional EDC economies the needs of users using the strategy provided in this paper. The transmission of delay traffic is guaranteed. That's all. Thank you.
Hello everyone, my name is Guo Long. I am from Chang'an University and School of Information Engineering in Xi'an. I am very honored to participate in the fourth EAI SGIoT conference and make a report. The main content of my report is about a new scheme of beamforming trimming in millimeter wave with WLAN. Let's begin our share time. The title of this report is Grouping-based beamforming beamform trimming scheme for the next generation millimeter wave WLAN. This report is divided into 5 parts: background, contribution, protocol design, simulation results, and conclusion. The first is the background. The implication of WLAN technology can make device connected to the network more. On this business, the millimeter wave WLAN protocol and the beamforming technology enables wavelength communication to support the transform of service with ultra-high data rates. But the problem of the conflict when state nodes perform beamforming trimming during the ABFT period is still not served. Therefore, we propose a grouping-based beamforming trimming scheme for recording conflict. The reason for this problem is no matter in any ABFT slot, because state is randomly selected into an ABFT slot, there will be n minus 1 states colliding with this node. In the IEEE 902.11ad, channel access process is mainly performed in beacon interval, and sub-segments of the BI are called the access period. There are 4 periods, like BTI, ABFT, ATI, and DTI. They have different access rules and coordinate access time through schedules. We mainly introduce improvement schedule in APFT period of beamforming training. The main work during the APFT period is beamforming training. In 902.11ad, states randomly enter the pre-allocated ABFT slot. In each ABFT slot, state performance sector level swap with all APs, and finally obtain the best standing sector or beam ID information of themselves. Uh, 902.11ad standard using beamforming training to solve the problem of high transmission loss in millimeter waves. before internals send the data packet directionally, performing periodic performing training before initiator and responder nodes to find the best sending and receiving beam IDs and achieve antennas alignment. The aligned node from a beam with multi-directive. This can effectively enhance the signal energy in the direction of demand link and also suppress interference signals from other links. In terms of workflow, beamforming trimming is divided into 4 stages: SLS and beam refinement phase. Since beam refinement phase is not in this improvement, the following will mainly introduce SLS stage and sector swiping method. In SLS, sector swiping uses an exhaustive method in which initiator swaps sectors from initial sector one by one until all sectors are swapped. As shown in figure, the AP uses N sector or beam to cover cell. In SLS stage, AP swap sector from the TX first to the TX in turn and send different sector information at the same time. States receive and measure signal energy emitted by different sectors and feedback relevant information of AP. According to the feedback information of states, AP determines the best transmission sector ID aimed at the states. The best AP sector ID pairs corresponding to state 1 and state 2 are TXI and TXN and TXG and RX2. The innovation of this scale lies in using IEEE 902.11ad protocol as an example for reducing conflict. The simulation results show that it can effectively reduce the collision probability of states during beamforming training and improve the throughput and packet error rate in communication. Now, let's introduce protocol design. In BTI period, we propose a grouping-based sector swap called GSSW for short. We propose GSW to assist GABFT race. GSW has 4 phases: GSD, EGSSW, require IGSSW, and IGSSW. In this figure, shows the GSW in one AP6 state simulation topology, where A is GSD phase, B1 and B2 are EGSSW and require IGSSW phase, and C is IGSSW phase. As shown in figure, AP sequentially enter different BTI slots and interact with all states by GSFW. In a BTI slot, AP first performs each GSFW phase, and then AP judges whether states need to perform IGSW phase through the feedback information. If necessary, AP use intragroup sector to send a narrow beam DMG beacon frame to state. If not, skip this stage. In APFT period, we propose a grouping-based APFT slot response response called GAPFT race for short. We stipulate that APFT slot are key states in APFT period are L, and all states are divided into M sector groups. AP has multi-beam receiving capability, and states of non-adjacent sector group can simultaneously access a same APFT slot. In terms of mathematical derivation, by compare the probability of conflict, we get G APFT race is better than without it. This figure shows G APFT race scheme in one AP6 state simulation topology, where A is the result of sector group B1 and B2 are GAPFT race exclusion stage in APFT slots. Among them, group TXA and group TXC are not nergensent, and group B and group D are also not adjacent. Figure shows that state I and state G belong to different sector groups, but they can enter a same before APFT time slot. This is because these two states belong to no adjacent sector groups, and they will not conflict during the beamforming training. This is a flow chart of overall scheme. As shown in figure, APFT period, the scheme uses G APFT race to reduce the collision probability of state and adopts GSFW to perform sector grouping in BTI period. Now, in simulation result, there is one AP, 6 states and 6 APFT slot, and the AP has 4 group sectors and multi-beam receiving capability. The table also shows other parameters such as bandwidth, survey business, and number of sectors. As shown in figure, when throughput reaches situation, situation, throughput after using GABFT race is about 6,000 Mbps and higher than unused GABFT race. This is because it reduces the probability of collisions between the states in ABFT slot, thereby reducing the time for re-beamforming training due to collisions. As a result, the number of successfully reduced packets are increased and throughput is also improved in same simulation time. This is PR. In this figure, when throughput reaches saturation, PR after using GABFT race is about about 0.01 and lower than unused GABFT race. This is because error packet number has not changed and GABFT race increased the number of successful raised packets. As a result, PR is decreased in same simulation time. We use 6AP and 36-state topology for simulation on page 20 to 22. The result shows that our scheme has successfully improved the throughput and PR. Finally, we can draw the following conclusion. Grouping-based beamforming training successfully reduce conflict probability and improve throughput and PR in millimeter wave communication. And in the future, we need to improve more analysis in other millimeter wave protocol, such as IEEE 902.11 AJ or AY. Thank you, everyone.
Hello, my name is Miao Qingyuan. I'm from Xi'an. Let's take a look at the title of this PowerPoint. NOMA-based RFID identification method. At first glance, we can know that it talks about two concepts: non-orthogonal multiple access and reduced frequency identification. This introduction consists of 5 parts from the structure. The first part is the background. The second part is the contribution. The third part details the method, and the fourth part simulates and tests the method. Finally, we do some conclusion. The following, we have to carefully analyze those parts. In this part, what we need to know is RFID is an essential technology in the Internet of Things, facing with a massive access request nowadays, and the operation characteristics different from human communications. There are higher requirements of the performance of the access terminal of the Internet of Things. Especially in dense deployment scenarios, it requires large system capacity and faster access efficiency. However, the traditional anti-collision algorithm hardly keep pace with the increasing demands. This is a brief introduction in this part. In this paper, the power domain NOMA is combined with tag inventory and access at a new algorithm of NOMA-based RFID tag identification method is proposed. The method complying with ISO IEC 18000-6 protocol standard as designed is universal. The simulation results the NOMA-based RFID tag identification method improves the RFID system performance well, improves access efficiency and system complexity. At the same time, the method of design and analysis constructed in this article has certain universal significance. Different tags are divided by SIC. The second is the presence of inventory at expense. The inventory command set includes query, query just, query wrap, and ACK. Query initiates an inventory route and decides which tags participate in the route. Query contains a slot called parameter queue. Upon receiving a query, participating tags pick a random value in a range. The queue power of 0 to 2-1, inclusive, and load the value into their slot counter. Tags that pick a 0 transition to the replay state and replay immediately with 16 random number. Tags that pick a no-0 value transition to the arbitrary state and wait a query just and query wrap command. The query just and query wrap can decrease the slot counter. And then interpreter acknowledges tag by SU in ACK with same 16-bit random number. If the number is self-generated, tag replay EPC and complete the identification process. This part details the method. Assuming a single tag replace, the query response algorithm proceeds as follows. Step A. The tag backscatters a 16-bit random number as it enters replay. The interrogator acknowledges the tag with a ACK containing this same 16-bit random number. The acknowledged tag transitions to the acknowledged state. Backscatting a replay with EPC. The interrogator issues a query just or query wrap, causing the identified tag transition to read and potentially causing another tag to initiate a query response dialog with the interrogator starting in step A above. Assuming more than one tag replace, the interrogator can only identify 1 0 at most, but can't realize the total identification. When there are more numbers of tags, so the probability of replaying 60-bit random number at the same time will increase as the number of tags increases, which will result in severe collusion. Why do we use NOMA to solve this problem? Interrogator is both the sender and receiver, so we don't need to cheat the complexity of the tag. At SIC, interrogator issues signal by using the identical transmitting power. Some tags responses the signal at the same time, because the distance from the SIC interrogator is different. The SIC interrogator will get a different receiving power because of the payloads. The SIC interrogator having normal uplink receive complexity, so the SIC interrogator can receive in multiple replay signals. The distinguishable power levels of system. All text at different power levels will be identified successfully. For example, like tag 1 and tag 2 and tag 3 and tag 5 will participate in the identification. They will all success. More than one text join in identification at the same power level, all will fail to identify. Like tag 1 and tag 2 and tag 3 and tag 4 take part in the identification. We can dim tag 2 to tag n and noise as the interface of tag 1, and select one signal throughout, make the system work properly. Text minus text 2 to tag n greater than throughout. They can be divided by NOMA. Deduce it. If all are satisfied, all tags can be divided by NOMA. There are three scenarios. Conditional deployment scenario. Interrogator acknowledges tag by SU in a ACK frame. Dense deployment scenarios. Interrogator acknowledges tags by SU in multiple ACK frames. In order to prevent the DOLIC from being congested by too many ACK frames, we design a new multi-ACK frame. It contains multiple frames of different 16-bit random number. Tag judges whether or not it is recognized by 16 random number. High density deployment scenario. Interrogator acknowledges tags by issuing a multi-ACK frame. This part is the simulation scenario. Different dense deployment scenarios like low density and high density. Interrogator is both a sender and receiver. The size of data packets at multi-ACK transmitted in the uplink or downlink is the same size. 2 power throughout streams, 6.9 decibel and 10.3 decibel. NS3 at MATLAB is used for our simulations. Constant transmission power. Perform several simulations and take the average value at the simulation results. This part is the simulation results. In Figure 6, it can be seen from the slot official graphs with Q values of 4 and 6. With NOMA is more efficiency than without NOMA. When the number of the tags of 24, the slot efficiency of without NOMA reaches the peak. When the number of tags of 52, the slot efficiency of with NOMA reaches the peak. The gain is about 185%. The red and the black. Look at the gray and the blue. Compare with Q value equal to 4. The gain is about 178%. When the efficiency reaches to 0, with NOMA has more tags. The efficiency of NOMA-based RFID tag identification method is more than normal methods in all different tag numbers. The algorithm has higher access efficiency, larger system capacity, and higher pig tag count compared with normal methods. In Figure 7, compare the slot efficiency with different signal thresholds, the red and the blue. It can be seen that the higher the threshold, the lower the efficiency of slot. The gain of NOMA-based tag identification system depends on the threshold setting, and different signal thresholds can achieve different gain effects. We will try different signal threshold algorithms to obtain the best signal threshold under the current system overhead. Finally, we do some conclusion. NOMA-based RFID tag identification method for RFID is proposed by combining the power domain, NOMA, and tag inventory and access percents. RFID system can identify multiple tags concurrently. At the same time, the method of design and analysis constructed in this article has certain universal significance. The simulation results turn out the desired protocol improves the efficiency of slot by 170% and expand the system complexity. That's all. Thank you.
Ladies and gentlemen, today I would like to introduce my paper. I am Cai Huan. My paper name is Coordinated TDMA MAC Scheme Design and Performance Evolution for the Next Generation WLAN IEEE 802.11be. My presentation will cover the following aspects: background and contribution, protocol design, simulation results, conclusion. Wireless local air network, for short WLAN, has been greatly developed for the last 20 years. Quality of service and quality of experience in high-dense development scenario greatly challenges the next generation WLAN. The next generation WLAN standard IEEE 802.11be aims at extremely high throughput, for short EHT, which is a big challenge for super density development network scenarios. This means that the number of cells is increasing and the competition between cells is getting bigger and bigger, and the inter-cell interfaces will increase. If APs work independently in this order, the inter-cell interface will cause EHT goal cannot be achieved. This paper focuses on the key technology called Coordinated Team Division Multiple Access, for short called TDMA, in IEEE 802.11be. Designs a specific called TDMA protocol implementation scheme, implements the called TDMA protocol processes, and evaluates the performance of this protocol. This simulation results the core TDMA protocol designed in this paper improves the delay performance while improves throughput and reduce packet loss rate. My paper core adheres in the data transmission. The master AP schedules the slave APs to share a TSOP transmission opportunity of the master AP. The TXOP duration of the master AP is divided into multiple time periods. The master and the slave APs occupy different time periods for data transmission. In this way, the master and slave APs share this transmission opportunity of the master AP. The slave APs can directly transmit data when the allocated time period arrives without competing for channels. The transmission scenario of the core TDMA mechanism is shown in the figure, where multiple cells jointly cooperated for data transmission. The core TDMA designed in this article is divided into 3 stages. The first stage is the master AP learns the business requirements stage of the slave AP. In this stage, the AP competing for the channel becomes the master AP. After the master AP competing for the channel, the master AP sends a broadcast detection frame to the other APs or other cell in the signal power coverage range to detect whether other cells have service to transmit. When the AP or other cells receives the detection frame sent by the master AP, the AP needs to relay an ACK responsible message to the master AP to information the master AP that the cell has service transmission requirements. The second stage is the master AP triggers the schedule process. In this stage, after the master AP knows whether all the cells have the demand of service transmission, the master AP decides the slave APs participate in the joint transmission through the decision algorithm under the condition of optimal network transmission, and through the time local algorithm, the time period occupied by the master AP and each slave AP in the TSOP transmission is calculated. After the information is ready, the master AP will send a trigger frame to each slave AP. This trigger frame carries the information of each slave AP in the cooperative transmission and the time period information occupied by the master AP and each slave APs. The last stage is master AP and slave AP's data transmission process. In this stage, if the master AP has service to be transmitted, the master AP takes the lead in occupying the channel for data transmission after sending the trigger frame. If the master AP has no service to transmit it, the master AP will remain silent after sending the trigger frame, and the other slave APs will access the channel and the start time point of transmission according to the transmission time period specific in the trigger frame, and the transmission service will be on time at the end of transmission intermediate point. The end of transmission, the use of the channel to other slave APs. The protocol process mentioned above is shown in the figure. AP1 is the master AP. AP2 and AP3 are scheduled as slave APs, and the code TDMA process is executed. Among the code TDMA protocols designed in this article, the setting of NAV is a very important issue because the messages between these in various cells are not interoperable. This article adopts two NAV setting methods. One is newly introduced a group NAV, and one bit is access channel flag bit. The station associated with the slave AP needs to update the group NAV after receiving the frame from the master AP. The station associated with the slave AP sets its access channel to true only after receiving the trigger frame from the master AP to allow access to the channel. Otherwise, it remains false after the station associated with the AP receives the trigger frame if the group NAV is set and the access channel is true. At this time, the group NAV is allowed to be ignored. Otherwise, it is not allowed to ignore group NAV, and it is not allowed to compete for channels. The setup process is shown in the figure. When state 2 accesses the channel, group NAV is set. Its access channel is true, then group NAV is ignored. When state 3 accesses the channel, group NAV is set. Its access channel is false. No access to the channel is allowed. The other is modified trigger frame. Use reserved bits in common infer. The state associated with the slave AP needs to update the group NAV after receiving the frame from the master AP. The one bit resolved bit in the common info of the trigger frame sent from the AP in the TSOP is set to 1. If a station judges after receiving the trigger frame from the associated AP, if this bit is set to 1, then a group NAV is ignored. If a station judges that if this bit is set to 0, after receiving the trigger frame from the associated AP, it shall not ignore the group NAV and counts responsible to the trigger frame. The setup process is shown in the figure. when station 2 accesses the channel. Group NAV is set. The reserved bit in the trigger frame is set to 1, then group NAV is ignored. Group NAV is set when station 2 access to the channel. The reserved bit in the trigger frame is 0, then access to the channel is not allowed. Perform simulation according to the simulation scenario configuration shown in the following table. Drive simulation results and analyze the results. When the simulation service rate is small, the throughput and packet loss rate of the core TDMA mechanism are basically the same as the EDCA mechanism. With the increase of the simulation survival rate, the core TDMA mechanism has higher throughput and lower packet loss rate than EDCA mechanism and has better network performance. Through the analysis of the simulation results of different service rates, the core TDMA protocol can improve the throughput of the inter-network and reduce the network conflicts in the sense of high density network development with high traffic. Although core TDMA reduces conflicts, it reduces the possibility of concurrent transmission. In future research, it is necessary to study the trade-off of core TDMA and concurrent transmission. Okay, ladies and gentlemen, it has been my pleasure to give you my viewpoints on concatenated TDMA, max game design and performance evolution for the next generation WLAN IEEE 802.11be. Thank you very much for your listening.
Hello everyone, it's my great honor to have the chance to attend the SGIoT 2020 and give a presentation of my paper, Secure Sharing Sensitive Data based on Network Coding and Attribute-based Encryption. Today I will introduce my paper from 6 aspects: author information, simple introduction, method, the model, experiment, conclusion. There are 3 authors of this paper, and I'm Xu Zhiqiang, come from the School of Electrical and Information Engineering, Beijing Jiao Tong University. First of all, I will give a brief introduction of my paper. The security of sharing sensitive information through a distributed information storage and sharing platform is required strictly in many situations. In this paper, we present a novel approach with the aim of increasing security of sharing sensitive information. The model improves security by exploiting attribute-based encryption. In addition, we incorporate network coding to our model to improve the efficiency of transmitting information. For the purpose of security, access control and data management are realized through secure association between multiple domains in general information systems. On the other hand, cross-domain access is often required to maximize shared network and data resource service, which are contradictory to each other. Because cross-domain access makes the management of users with different security domains and different security levels more and more complex, and various applications they approach vulnerabilities give hackers opportunity to attract the network. Therefore, it is very important to study the security sharing theory and the technology of sensitive data in view of the application of multi-level security cross-domain sharing of data, and realize flexible cross-domain data access and improve the availability of data under the condition of protecting sensitive data from leakage. Researchers have made a lot of work about encryption and network coding, and I will introduce some examples briefly. Shamir first proposed the concepts of identity-based encryption. They introduced a novel cryptographic streaming, which enables any pair of users to communicate securely and to verify each other's signatures without exchanging private or public keys, without keeping key directories, and without using the service of a third party. However, it wasn't until much later that Bernie and Franklin proposed the first fully functional encryption scheme that was both practical and secure. Shahi and Waters proposed a new type of identity-based encryption called fuzzy identity-based encryption as a new means for encrypted access control. Bonicott provided the first construction of a ciphertext policy attribute-based encryption (CPABE), and gave the first construction of such a schema. In their system, a user's private key would be associated with an attribute number of attributes expressed as string. Oswald also proposed a new class of problem called network information flow, which is inspired by computer water applications. In the following time, I will introduce the main methods used in our system. Firstly, CPABE. There are 5 steps of the process of CPABE. First of all, we need an implicit security parameter to generate the public parameters PK and a master key MK. Secondly, when we want to encrypt a message M, encrypt PK MA can output a ciphertext CT. Then we should use the key generations MKS to generate private key SK for every users. Finally, user can use his private key SK to get the message M through the function decrypt PK CT SK if the SK satisfies the access structure A. Secondly, network coding. Network coding is a novel technique proposed in 2000 which can improve throughput and the performance of network. With the appearance of network coding, a simple but important observation was made that in communication networks, we can allow nodes to process as well as forward in the incoming independent information flows. While an intermediate node gets some independent data, it can make a binary addition before transporting them. Handling these independent data streams can greatly improve the efficiency of network information transmission. It is a cheap computational power, and the network coding utilizes to greatly increase network throughput. We will give a simple example to show how does network coding improve network throughput when multicasting. As we can see in the figure, a communication network represented as a direct graph. Vectors represent terminals and edges represented channels. This communication network is commonly known as the butterfly network in the network coding. Assume that we have slotted time and that through each channel we can send 1 bit per time slot. We have 2 data sources S1 and S2 and 2 data receivers R1 and R2. Each source produces 1 bit per time slot. Data X1 is produced by S1 and X2 is produced by We consider a situation called multicasting that receivers R1 and R2 want to receive the information from sources S1 and S2 at the same time. When it comes to this situation, receiver R1 can receive X1 from source S1 through the path AD, and the receiver R2 can receive X2 from source S2 through the path BF. But we want receiver R1 can get X2 from source S2, and the receiver R2 can get X1 from source S1 through the path CE simultaneously. However, we can only send one bit per time slot, and we want to simultaneously send bit X1 to reach receiver R2 and bit X2 to reach receiver R1. The simple but important observation made by us with is that we can allow intermediate nodes in the network to process their incoming information streams instead of just forward them. In particular, node C can take bits X1 and X2 and create a third bit X3 equals X1 plus X2, which it can then send through HCE. R1 receives X1 and X1 plus X2 and can serve the system of equations to retrieve X1 and X2. Similarly, R2 receives X2 and X1 plus X2 and can serve this system of equations to retrieve X1 and X2. This example shows that when multicasting, we can improve throughput through the allowing intermediate node in the network to process information streams and receivers existing the information. In addition to the improvements of throughput, the security of network coding also has advantages. Instead of sending uncoded data, sending linear combinations of data can offer a natural way to use advantage of multipath diversity for secure against wiretapping attacks. So we only need protection against other attacks with network coding. However, there are some challenges to deploy the network coding. First of all, the complexity of employing network coding is high because the nodes in the network need to have some additional functionalities. For example, the intermediate node has additional memory and calculation requirements because instead of broadcasting strings immediately, it needs to store and process strings. Another challenging task is to incorporate the emerging technologies such as network coding into the existing network attributes. We describe our model in this part. In our simulated file transfer system, we have one controller server and 7 file servers, and the connection topology is shown in the figure. Each file server is connected to the controller server. These file servers are server nodes in different networks, representing system nodes which are located in different areas. Every server node stores a variety of encrypted files in the initializing pairs of the system. All the file server nodes first establish a connection to the controller and then transmit some information to it. The information is about all the local file directories and the connections to other file server nodes. When the controller receives feedback information from each node, it will summarize information. Through connections of each node, the controller can get the whole file system nodes connection diagram. In the same way, after receiving every node's local file directory, the controller can generate a list of all the files existing in the system, which consists of two parts. The first part is a map in which nodes each file located, and the second is the directory of every node. In order to make our system has the ability of resisting some disasters, we follow the idea of Hadoop's, which is making 2 copies of all files. That is, choosing for each file has 2 backups distributed in different nodes of the system. This approach has great benefits for the system. Another important task in the system's initializing phase is to assign private key of ABE to each server node. We need to be aware of every server node's attributes due to use of attribute-based encryption in our system. We set default properties such as the form of node ID. For example, node 3 has the attribute as a string of node ID 3. After determining the attributes for each node, the controller generates private keys with the corresponding attributes of each node through key generation algorithm in APE, and then send the private keys to related server nodes. When the controller assigns the private keys to server nodes, it is not allowed to send the plain text directly. Our system uses SSL, secure socket layer, to distribute private keys. SSL is a protocol for the secure exchange of information between TCP connections, which provides two basic security services: Authentication and Confidentiality. We can safely send the private keys of APE to each file server node through the controller with SSL methods after finish proprietary work. After the initialization of the system is completed, we can start file sharing. If user needs one file, he needs to issue a request contains the desired file's name to the closest file server node to which he connects. When a server node receives the request of file, first it will research that file locally. If server node has this file, it sends to the user directly. If this file is not available locally, the server node will send the file request to the controller in the form of desired file's name. After receives a file request, the controller will search through the list of all files according to the desired file's names to find where it is stored. When it comes to multicast, first of all, the controller calls the minimum cut maximum flow algorithm of network coding to find out the path of transmission. Then the weight matrix is calculated by the weight calculation function in the network coding. In the following time, the configuration information will be sent to corresponding server nodes according to the path. After receiving configuration information, these nodes will prepare to receive and forward files as required. Controller can choose the encryption policy according to the attributes of users who requires files. The policy will be sent to the first server node of the path. Starting node divided the file into some parts in setting size. For example, we set the block size of 100 MB. Every part will be encrypted by APE with a header which records the location of each part. UDP package is used in the sending process, but only after receiving the confirmed message from receiver. The sender side can continue to send the next package. Moreover, we have set up a simple verification and retransmission mechanism to ensure the high transmission quality of a file. When get some byte trees, the receiver puts it into a queue and enables another thread to process bit strings according to the configuration information of network coding and forwards it. Sending and receiving are separated. After receiving all the segmented paths, each server node extracts information with network coding algorithm. Then it will decrypt the segmented part using private key and recover the complete file according to the header. In the next part, I would like to show you some experimental results of our system. We evaluated it on two security effective of network coding. The system security of this paper mainly consists of two parts: the security of private key distribution and the security of file sharing. For key distribution, SSL is used to transmit private key securely because of its bidirectional authentication function. We use network sniffer tools to monitor the traffic, which is found that all the data transmitted is garbled in the process of private key distribution. Then we can guaranteeing the security of key distribution process. In addition to the security of key distribution, it is also necessary to ensure the security in process of sharing files. We use ABE to encrypt the transmitted content because, as required in distributed systems, the data can be accessed correctly only if the user satisfies some particular attributes. However, there is a risk that the server node will be attacked if files are not sorted on it. Then we use CPABE to ensure access control. The decryption policy is under the control of the controller node, so that even if the server where files are stored is attacked, it can be protected. We want to verify the efficiency of network coding in multicast. In this grid, we respectively transfer two different files from node 1 to node 3 and node 7 to record the speed. Each node stores 50 to 100 files ranging in size from 1 MB to 5000 MB. We change the size of the transferred files and recorded the time required for transforming two files under the two methods of using network coding and not using network coding for comparison. The results are shown in the table 1 when two files are in the same size. The results are shown in the table 2 when one file is half the size of the another. As we can see in the experiment, the transferable efficiency of using network coding is higher than not using it by almost 11% when two files are in the same size. But when one file is half the size of another, the efficiency improvement is decreased to almost 6% because of the limitation of network coding, which is that it is most efficient to transfer files of the same size. We can get the conclusion that using network coding can improve transferable efficiency in our system. The final part is about conclusion. In this paper, we proposed a system for share-sensitive data security, which are based on attribute-based encryption and network coding. Our system uses a new type of encrypted access control where users' private keys are specified by a set of attributes, and Apache encryption data can specify a policy over these attributes, specifying which users are able to decrypt. We also use network coding in our system to improve the efficiency of multicast. One limitation of our system is that ABE is proved secure under the generic global heuristics, so the security of our system is limited in some situations, but we believe some more secure technologies which can be applied to our system would be proposed in the future. That's all, and thank you for your listening.